talked about how we can use them. Not necessarily a lot of people use them. I mean, some people in the mill may or may not use them. I think it's a tool we should use quite often, whether we're in projects or in service. It's a handy tool. It's easy for us to calculate because we have tools that calculate it for us. You don't have to go through the math and figure it out on your own. So it's really easy for us to generate these things. And if you understand about them and know how to interpret them, they're kind of a powerful thing. The third one on the list there, autocorrelation. In my mind, that's a little less useful than the other two. Again, it's easy for us to calculate because we have tools. Is it useful? Maybe. You know, it can do, power spectra can do generally what autocorrelation can do in a different method, but autocorrelation can't do what power spectrum can do. So maybe the power spectrum is a little more useful than an autocorrelation, but autocorrelation has usefulness. And there's something else that's not up there that I'll talk about too, cross-correlation, which is another version, if you will, of autocorrelation. Actually, autocorrelation is a specialized version of cross-correlation. Cross-correlation is handy, and we can use that, and we can choose to use that as a tool in our toolbox. Autocorrelation, maybe you don't need to use that so much. And in my experience over the years and doing this stuff and doing analysis and reports and things, I use 2 sigma all the time. I use power spectrum all the time. I don't use autocorrelation that much. Sometimes I use autocorrelation to confirm what I think I see in the power spectrum, and we'll talk a little bit about that. Effects of sensor dynamics and signal processing. We'll talk a little bit about that and how it affects us. We'll talk about aliasing, as I mentioned, and one specific example of aliasing that pops up that, as I say, will trip us up if we're not careful. It's important to know when the numbers are valid and how that affects us. You have to get a feel for, is your data good, or is your data showing what you think it's showing? And maybe that's 50% training, 50% experience. And I can't give you the experience today, but I could at least go through the training part of it today. So here's a nice graph to try to help explain what 2 sigma means. So let's start that to say that, first of all, 2 sigma is 2 times sigma. Okay, that's easy enough. But what the hell is sigma? Well, 3 sigma is 3 times sigma. But what's sigma? Well, that is a formula for sigma. And that's fine. If you want to calculate it yourself in Excel, you can get a whole bunch of data and you can plug a formula in and calculate it. But I find it's easier to explain to people graphically. If you have a data set, and this data set can be a data set of anything. This could be a 90-point profile, or for that matter, a 1,000-point profile. This could be 90 scan average values from a scanner. This could be 90 1-second values of stock flow or some other flow. It doesn't matter. It's a data set. It's a bunch of data. That data has a mean, okay? A mean or an average. That's easy to calculate. I think everybody knows how to calculate the average of a data set. What this sigma is actually, the sigma is another word or short form for the word standard deviation. So when we say the 2 sigma equals 20, like I do here, what I'm also saying is the standard deviation equals 20. And I'm referring to the dispersion of the variables around the mean in this data set. So by saying that 2 sigma equals 20, there's actually a predefined value for what 2 sigma represents. And if I go to the next slide to show you those numbers, 2 sigma represents 95.5% of the data. 1 sigma represents 68, and 3 sigma represents 99.7. We don't talk a lot about 1 sigma and 3 sigma, although Valmet paper likes to use 1 sigma for their guarantees. That's their thing. And I know a couple of mills use 3 sigma. Yeah, right. But generally speaking, we all use 2 sigma. And so that 95.5 is an important number to keep in the back of your head. So let's go back to this and look at this.
Why does Valmet use 1 sigma?
I honestly have no clue.
Smaller
number.
That doesn't matter. It's a convention.
It's their convention.
Yeah.
And so when we're in a guarantee situation with them, the guarantee is going to be quoted as a 1 sigma guarantee. It has to be X.
But it's easy to meet that.
If you know 1 sigma, you know 2 sigma.
Yeah, exactly. If you know 1 sigma, you know 2 sigma.
Well,
But no, it's easy to meet that guarantee, isn't it?
It's true in a normally distributed.
It's a true and a normally distributed set of data. And we have to assume that our data is normally distributed.
It's a bad assumption to begin with.
Well, and another assumption we make, and I'll mention this now before someone asks me the question, is for this formula to hold true, you have to have a minimum number of data points. You can't run this formula on 3 data points. Okay? Now, having said that, if there were project engineers in the audience, I would ask, how many people have done a sensor correlation with 7 or 8 data points and run a 2 sigma. And they'd all put their hands up. So although, mathematically we know that's cheating and that's not following the rule, we do it.
It's not
accurate.
Bigger confidence interval.
Exactly. It's like 25 is a rule of thumb.
Yeah.
In a normally distributed
Right.
population, you'll get the right number.
Exactly. Our data is not necessarily normally
The
distributed.
n minus 1 will actually overestimate. So
Yeah. So it's close enough.
Yeah.
And that's what I wanted to say, is that the 25 data points is a close enough. The normally distributed is a close enough. Okay? It's not perfectly statistically accurate, but it's close enough. For our purposes, it's more than close enough. We have many other issues that make our data less reliable than that.
The definition of 2 sigma applies whatever distribution you have.
Yes.
Normally only refers to those numbers that you have seen.
Right.
Otherwise, there is a need for measuring the dispersion of data, which is this definition. And this is sometimes called, if you go deeper, it's called first moment of the distribution. Then there is second moment, third moment, fourth moment. So you can actually describe a distribution in many different parameters, or you can describe it as a plot like this.
Right.
But a plot like that doesn't lend itself to easy communication when you're doing guarantees, blah, blah, blah.
The number is the easy
So
communication.
let's understand that.
Yeah. And what I'm saying here, when I say the 2 sigma of this data set is 20, what I'm saying is that 95.5% of the numbers in the data set fall within plus or minus 20 of the mean, which in this case is 50. So in this particular example, between 30 and 70, that range contains 95.5% of all the numbers in my sample set. And that's what 2 sigma, or that's what sigma means, or that's what 2 sigma means, and that's what people say when they're talking about it. Now, the one potential gotcha here in this whole talk about sigmas, or 2 sigmas, is that you need to know what the data set is relative to the 2 sigma. So if I say to you, the 2 sigma of my basis weight is 25, what does that mean? Basis weight what? We're talking about scans, profiles, 1 second data, 5 second data, data for a year, data for an hour, and the thing I see a lot and heard a lot, and hear, and still do hear a lot, is people are very quick to say, oh, my 2 sigma is 25, what's yours? Yours is 20, obviously it's better. Well, it might not be, because you never define in detail basis weight of what, or what kind of data set.
You at least need to know what the mean is.
Well, there's that too. Yes, yeah, that's a good point, because the 2 sigma of 20 on a 500 gram sheet is very different than the 2 sigma of 20 on a 40 gram sheet.
Right, exactly. Yeah.
There's that too. Yes, Chuck.
One of the most practical issues that I've seen related to this comes when we put in new scanners.
Yes.
And as part of the sales process, the boneheaded salesman doesn't remember to clue his customer in that his new scanner is going to give him a bigger 2 sigma.
And we
And at startup we find out, oh
I think
shit.
we're a lot better now.
Yeah, and at startup we find out, oh shit.
We should have
I have a slide about that
You
later
know by
on.
the square root then.
Yeah.
Well, but what it is, they've got to go through the process of either planning for it prior to that. They've got a customer
And I mean,
matter that they can't report the new 2 sigmas to the customers so they
Yeah.
you know what I'm saying.
yeah, because
So-
we have cases where, because the mill is using our 2 sigma data to accept or reject their product to their end user,
Right.
and they don't want to change their acceptance tolerances, we've had to make lower resolution profiles to sort of calculate 2 sigmas like it used to be to make them comparable so they can run them through their acceptance
Right,
criteria.
because they had an old pair of glasses that they couldn't, or they had astigmatism or
Yeah,
cataracts
because
or
otherwise
whatever.
all of a sudden the 2 sigmas bigger, everything would quote unquote fail, even if it's really better in reality. And these are minor points, but they're gotchas. They're gotchas in a guarantee in a
Right.
sales space. They're gotchas in a project when you try to prove the guarantee, because maybe you didn't understand what 2 sigma they were talking about. They just said basis weight, and you weren't sure if it was high res, low res, 1 second data, 5 second data, MD, CD, whatever. You just knew it was basis weight. So these are little fine points that it's easy to miss, and they're going to hang you up if you miss them.
I just think it needs to be a standard part of the
Well, then I
sales.
have a slide on that.
Okay.
See, it's the same as all the other presentations. Everybody's 5 steps ahead. So anyway, those are our common thumbs up rule, and we missed that in the back there.
Is that a test to see who's paying?
This is a test to see who's paying attention. And
So the first row
isn't.
is 5 steps ahead, 4 steps ahead, 3 steps
That's
ahead.
right. So anyway, 1 sigma,
Fraction.
68.3%, 2 sigma, 95.5, and 3, 99.7. And obviously there's 4 sigma, 5 sigma. You hear about 6 sigma.
Hey,
You
I'm
know,
a Greenville Six Sigma.
Yeah, you hear about that's 99.9999 or something. Anyway, we're not quite at that level yet. So, one thing, and we talked about this sort of in other presentations, or we alluded to this in other presentations when we talk about ROI, is, okay, so you reduce the 2 sigma, so what? That looks nice, I guess, because we understand 2 sigma measures variability. We make the 2 sigma smaller, therefore our variability is smaller. That sounds good in theory. How do you turn that into ROI, or what do you get out of it? Well, you can get this out of it, this target shift. If we go back to this example here, if we go back to this example, one reason, this is their process, whatever it is, I don't care what the process is. They operate their process in this way because they have some actual constraint that they can never violate, whatever that is. And so in order for them to never violate this constraint here, they run the process in such a way that they can guarantee that almost everything is going to be good. And they're fine with that. Is it efficient? No. But that's the way they run things. And it has a 2 sigma. So we come along and say, we have a new control, we'll tune it, it'll be really great, we're going to reduce your 2 sigma by a certain amount, cut it in half. Well, when we actually cut it in half, what you notice to the distribution is that it becomes narrower, right, because the 2 sigma is smaller. And that's fine, but what the customer can then do with that is he can implement, in theory, this target shift. If we look at his blue graph and compare it to the green graph, by reducing the 2 sigma, we've allowed him to shift his set point from whatever that number is, 51 or 50 and a half, down to, let's say, 42, 45 or something like that.
5 pounds.
He still meets his final ultimate constraint, but he is allowed to save whatever this variable is. Maybe it's basis weight, he saves fiber. I don't know what the variable is, it doesn't matter what the variable is. He can do a target shift. Target shift can be equated to money. Now, we talk about, being very careful when we do guarantees that we're more than willing to guarantee a 2 sigma, but we have to be careful if we start guaranteeing the money. Because the only way you get the money is to do the target shift. I remember Steve showed, I think it was Steve, that showed one of the ROIs how, they were able to say, they can save $88,000 a year or whatever it was. Okay? They're only going to save $88,000 if they do that target shift. Okay, if they for whatever reason refuse to do it or they don't get around to it or whatever, they haven't saved any money yet. Okay, in theory they'll save 88 grand if they do the target shift. So while we can tell them you have the potential to save 88 grand, or we will guarantee we'll cut your 2 sigma by 30% or whatever, we typically want to stay away from the money side because of that exact reason. We cannot force them to do the target shift.
We don't want to stay away from the money.
Well, we don't want to guarantee the money, in my opinion. We can give them the potential savings of 88 grand, but I don't think we can put in the contract, we guarantee you will save 88 grand. Unless you force them to do the target shift. But I don't think you can force them to do the target shift. Right? You can say the savings potentially will be $88,000 if you make a target shift.
You say we want to stay away from that.
Well,
but I'll give you lots of cases. Bleaching controls, for example. That's how we make the quote. We use this target shift.
That's because there's without shifting the target, there's money to be saved in bleaching control just because of the non-linear.
But if you move the target, you get the chemicals.
Right. If you move the target, you get the money. But if you don't move the target, you may not, or you won't get all.
You need to let the mill know what that money is.
Yeah, I'm not saying don't tell them what the money is.
About his money.
I'm not saying don't tell them what the money is. Yeah.
You make these changes.
Right. I'm not saying don't tell them the money. What I'm saying is don't say Metso guarantees by December 31st you will save $88,000. Right. Regards, Lee.
And Jay's going to start it up.
Go on and introduce the concept of capability, process capability, or
Not really a lot. So that's what you're going to. That's what the idea is to get out of this 2 sigma is a target shift, which can then turn into an ROI, which can then turn into potential money, which can turn into payback, therefore a sale. In the old days, saying the 2 sigma was smaller was good enough. These days, that's not enough. I mean, it's still enough in some cases to say the 2 sigma is going to be cut, and they'll take this from it. They'll say, okay, well, if the 2 sigma was cut, I'll figure out my own ROI and how much money I'm going to do and blah blah blah. Not your business, maybe, but it's not always. Yeah, they don't want to tell you their internal costs and things, so they say it's okay. That's all I need. I'll do. But other places will let you do it, or even if they don't let you, you can do an estimate to them and give them an idea of the magnitude of the money we're talking about.
to put this into that perspective, all of our ROI calculators have the provision how much that cost is in terms of dollars, but you may not get to calculate it to that level. As long as the mill knows the Two Sigma and you told them, just plug in your cost number here, you're going to get the dollar value.
And I remember I did an audit down in Brazil back, I don't know, maybe it was 10 years ago now or more in Aracruz. And I went through, come up with all the Two Sigmas and stuff in the power spectrum and blah, blah, blah. And then used those ROI calculators. And basically, I didn't know the cost structure in the mill, and they weren't going to tell me. But I said things like, well, if your production cost is X dollars a ton, then you would save Y. And then they can take it from there. You know, they know what their real production cost is. They can do the math and figure out what.
Say it's not hard. They figure out if you tell them you can do a target shift and you save 3%.
Yeah, they know what.
You have to take that 3% times your production cost.
Right, but they know what their production cost is. I don't. Right. The point was I didn't, but I wanted to get the number in front of their face, so I did some research and got like an average production cost and said, well, if your production cost happened to be $1,000, then you're going to save this much. But I don't know what it really is. And we used that. One of the things we did was we used that to prioritize. They had 4 machines, and I did it on 4 machines or 3 machines, and we used it to prioritize which machine should we do first. Because they said we want to buy systems, but we don't know which one first. I said, well, we'll buy whichever one has the higher bang for your buck, even though I don't really know, but I know relative to each other what the bang for the buck is, so we'll go after that machine. Because you may not know. Anyway, that was a sideline. Now, something to be careful of, however, when calculating Two Sigmas. It's very easy to go into a mill, set up our QMM data collection software, let it run overnight, and go home, or go back to the hotel, come back tomorrow morning, load it in, run a Two Sigma, it takes you like 10 seconds, I got a number. Yes, that was easy, wasn't it? But, okay, for example, here's a trend of data. Might have been a grade change, I don't know. But either way, they were running 50 grams, pounds, whatever it is, for a while. Then they went up to 55 for a while. If you don't notice that, because you don't look at the data, and all you do is you have a big data string, you run it and you calculate Two Sigma. Two Sigma's 4.9. Wow, that's a big Two Sigma. I'm sure I can reduce that a lot, because I'm really good. I'm going to guarantee the mill that I can cut that Sigma in half or something, or even less, because really the Two Sigma should be like 2. So they're really way screwed up. I can fix that. So you didn't look at the data. You come up with some kind of guarantee like that. Now it comes time to do the project. You collect some before and after data. But when you collect your before and after data now, you don't catch this grade change. So you can't collect data in Two Sigma's 2 or 1.9. And then you go to try to tune it. And all of a sudden now you haven't fixed their Two Sigma by anywhere near as much as you thought you could. And maybe you don't understand why. Maybe you realize your mistake. Maybe you don't. But all you know is, oh, crap, something's wrong. I made a mistake. So I caution people when you're collecting data. It's easy to collect tons of data, far more data than you need, but you need to look at it. And you need to watch out that you don't accidentally trip yourself up by doing something like this inadvertently.
You need to understand it in context.
Yeah, right.
I would tell you anytime you calculate Two Sigmas, it's a profile, plot a bunch of profiles.
Yeah, look at them.
A trend, plot the
That's
trend.
what you got to look at them. Because otherwise,
And even if you did your histogram,
it would have been, well, funny you should say that. Because even if you did your histogram on this, you would see that. And remember our rules about Two Sigmas. We say that the closer you are to this normal distribution, the more accurate the number is. Well, that's pretty far from a normal distribution. So that you can calculate a Two Sigma. It's just math. Of course, it's not going to be representative of reality because that's not a very normal distribution.
But as Sagan said, even if your data isn't normally distributed, Two Sigmas still displays.
Yeah, of that it does.
Of
Of this data set with the 2 levels in it. The problem you get into is when you go to look at the data at another time in the future and it's not got the 2 levels. It's 1 level. And then they're not comparable. And that's another thing to mention, this comparability of data. Don't use data, let's say, 128 profiles points, you have to calculate a guarantee, and then go prove it on a 1,000-point profile. You have to compare apples to apples, otherwise you're going to get yourself into trouble.
Since Steve pointed out, I'll say the other thing. I say, look, the moment of distribution, second moment will catch this one.
Yeah.
So, funny that you mentioned that so conveniently, because I had this slide waiting. Anyway, here's another thing along the same lines of same Two Sigma, different data. Those are 3 data sets. The green line is a step change. And I'll mention that, some people might describe a step change as a sine wave with an infinitely long period, maybe.
Only a mathematician,
Okay.
Only about-
not an engineer.
Anyway, it's a step change. Okay, the red line is a sine wave, and the blue line is some data with noise in it, more realistic data. The thing is, all those three data sets happen to have the same 2 sigma. So if I was making a report of any kind for a project or a service visit, and all I did was say, the 2 sigma is 1.41. That was what my report said, those words, and I didn't do any graphs. Maybe I never looked at the data myself even. Or maybe I looked at it but said it's not important to make a graph for the mill. I'm just going to tell them the number because they just want the number. Our guarantee says 1.42. I'm going to tell them the number. It's 1.41. We're out of here. We meet the guarantee. Well, yes and no. Depends on what your data really looks like. If you got 1.41 and your data looked like the blue line, then yeah, you probably just barely met the guarantee. On the other hand, if you got 1.41 and your data looks like the red line, well, numerically you met the guarantee, but you've left the process in not a very good state. And if you got the green line, then I don't know what the hell your 2 sigma is but it's
That's great process control.
Yeah, exactly.
There's a great change, it's perfect.
maybe you collected the set point instead of the measurement by accident to do your calculation. Anyway, this goes back to the look at the data. Okay, look at your data, understand what you're calculating a 2 sigma of. Don't just blindly say 2 sigma. And the other thing about 2 sigma is quite often 2 sigma is not enough information to accurately describe the situation. It goes back to what I said a few minutes ago, my 2 sigma is 25. Okay, what does that mean? It really means almost nothing. I'm sure if I went to any system, I could find some 2 sigma that was 25. Doesn't mean the system's good or bad. It just means I can find some data set that has a 2 sigma of 25. What the hell does that really mean? So we need more sophisticated methods to describe the data, and that's where this power spectrum and autocorrelation comes into play, or comes into use.
But the 2 sigma, when you talk to a customer, you have to define what it's based on.
For sure.
For instance, the competition of Honeywell is always real actual
Yeah.
speech.
Yeah, and we have a slide on that a little later. That is important. That's very important, because without that,
Will never match.
yes, without that you're going to be in trouble. And quite often you get questions from customers where they say to you, let's say you do a project group, this is getting a bit on the sideline into more detail, but it's relevant, is a customer says, okay, well, I got your report, and you report on the 2 sigma of the basis weight profile is 1.5. Okay, but look, let's go to the system right now. Look at that display. Look at that operator screen. There's a 2 sigma. That's not 1.5. What, was the working yesterday and all of a sudden doesn't work today? What are you talking about? That's a 2 sigma of a different thing. Of course, it's not the same number, but they don't understand that because they don't realize that. And you know what? Probably some of our guys don't realize it either. But that's this whole understanding. You need to define what is it the 2 sigma of that you're reporting, and it needs to be clear to you when you make the report and to your audience when you present the report. And even more so in the guarantee document, otherwise you're dead. So I've had projects where it wasn't clear in the guarantee document, and I had to go through all these hoops, how to explain to the customer why the 2 sigma I'm reporting is probably the right one to report, but I know it doesn't match your guarantee number, but let me explain why. And I had to basically spend a day with this kind of stuff with the customer, conning him and convincing him and explaining him how. No, well, whatever. No, but he could, say, yeah, but your guarantee says 4. You don't meet 4, I don't sign. And you have to understand it. I think George said this in the project manager meeting, how having an educated customer is good for us, and it's true. If he understands, it's a lot easier. If he doesn't understand, then he's just going to cause trouble for him. So this is a perfect case of this. You got to make sure they understand, and even more so with power spectrum and autocorrelation. Everyone thinks they understand 2 sigma. And maybe they do, maybe they don't. But as you start to use other tools like this, how many people in the middle understand what a power spectrum is? Maybe 30% of the audience that understands 2 sigma. Right? So you got to be careful about using this stuff, or if you're going to use this stuff, you got to explain it. Make sure, again, your audience understands what you're showing. Otherwise, they look at the graph with a blank face and like, okay, whatever. I don't know what that's saying. This is the same data again. Our red, green, and blue lines plotted in a power spectrum and then in an autocorrelation. One thing that's interesting is because these are frequency methods, the data looks different and tells us different stories. Okay, so we know, and we'll get back to that slide in a moment, but we sort of know that 2 sigma doesn't tell the whole story or doesn't tell enough of the story. Sometimes we need to go deeper than that. How fast are things changing? What else is going on? Can we control it? This whole capability, which I'm going to talk about briefly, we can measure the capability of an MD control and a CD control. We can estimate that and determine what kind of improvement we hope to get if we implement this control, and that's what we do in these guarantees. Is we collect data, we run some tools on it, we get an estimation of what we think the capability is, and we say, based on the capability, theoretically you could reduce it by 10%, and then we quote 5 because we want to cover ourselves, and that's how we do it. So this is important to understand, and that's why we look into the spectral domain. So to define what a power spectrum is, I like this graph here, or this picture, because here's a data set. Again, this data set may be MD data, could be 5-second data, 1-second data, 30-second data, doesn't matter. This could be a profile, doesn't matter, it's a data set. Power spectrum works on MD or CD, it's a data set. If you look at this data set, we can break it up into pieces. You can kind of see this big purple wave in it. You can kind of see this green sine wave going through it. You can see this very high frequency red sine wave type thing. And then there's some noise too. Now, what I wish I had a marker to draw on this board, because when I do the course, I always draw on the screen to do this next part of the course. So it's going to be a little awkward, especially for the people who are remote, as I try to do this. But what's important to know is the relative amounts of these different signals within your main signal. Because some of these signals are controllable and some are not. And if we think about, I find it easiest to explain this in a CD context. If we think about a CD control, so this blue thing is a profile here, and it's made up of these pieces. A CD control is limited by the response of your actuator. If your actuator is a certain width, you can't control things narrower than the actuator. Actually, you can only control things even wider than the actuator. You can't even control things as wide as the actuator. Sometimes you can, sometimes you can't. But there's a cutoff point where anything that's too narrow you can't get rid of for simplicity's sake, and anything that's wider you can. It's not a straight cutoff, it's not that simple, but for simplicity's sake, we'll say that's what it is. We look at this graph and we assume that this big purple wave on the top is worth 80% of the variability in the signal, and then 10% for the rest of these 3 pieces. The next 3, the green, the red, and the noise. Okay. Am I more than 100? Okay, 70 and 3. 70, 10, 10, 10. Yeah, anyway, 70, 10, 10, 10. So if we had an actuator that was sized appropriately, that we could remove all of this purple variability, but none of the green or the red or the noise, then you could very simply say we could probably reduce 70% of the variability in best case theoretical scenario from your signal. Now in real life you probably are not that good, but for now let's talk theoretical. You reduce 70%. Let's say the distribution of variability was different. Let's say it was 70% of this little fine noise at the bottom, and then 10, 10, 10. 10 of the red, 10 of the green, 10 of the purpley color. Let's say that was the distribution. You have the same actuator. The actuator can only remove this top graph of variability. Well, in that case, now you can only remove 10% of the variability in the signal. That's a very different guarantee level. So what's important to understand is the distribution of variability within the signal, because that's going to lead you into getting a guarantee that's realistic. You know, you could use the so-called Honeywell method and close your eyes and say, yeah, I'll guarantee 10%, done. Sign the contract. But we try to avoid that. We try to make it a little more careful and scientific. What is a power spectrum really in 25 words or less? Well, in 25 words or less, the power spectrum shows the relative amounts of variability in your signal at different frequencies. So we look kind of like a graphic equalizer on your stereo. When you have a graphic equalizer on your stereo and the music is playing, all those bars are going up and down and moving, because as the music plays, the frequencies of the sounds change, and some are more and some are less. And so same thing with the power spectrum. This is bottom x-axis here is frequency. This is amplitude. The y-axis is amplitude. So if we look at this red graph, you see there's 3 peaks at certain points. So there's a lot of variability at this, I can't even read the number, but I don't care what the number is. A lot of variability at that point. There's a fair bit of variability at that second point beside it. There's kind of low variability, almost zero in this middle area. And then as we get more to the right, there's another peak that has some variability, but not as much as the others. The area under the curve of the power spectrum represents the total variability in the process. If we think back to our graph with the different colored sine waves from the previous slide, and we go back and say, remember I said if you had an actuator that could get rid of only the widest one, what would that do to us? Well, you could plot that on this graph. If you knew that width that your actuator could get rid of, that would be a number somewhere along here. It would have a certain frequency. And again, nobody can see my pointer doing this, but I'm pointing beside these two big peaks on the left side. And so you could draw a line there and you could say everything, the wider streaks, which are lower frequency, which are to the left of this drawing, I can remove. The narrow streaks, or the high frequency, are to the right of the drawing. I can't remove it. So again, depending on the distribution of variability in your signal, you can figure out what things you can remove and what things you can't remove. You can even, through the tools, do simulations to show what the power spectrum might look like after you remove the variability you can remove. And you can even calculate a 2 sigma from it. And say, now our 2 sigma is this, but if we could remove this variability, then the power spectrum would look like this, the profile would look like this, because you can calculate that too in the tools, and you can say, and we estimate how the 2 sigma would go from 0.7 down to 0.5, or whatever it is. So there's all sorts of tools to do that. We're not going to talk about them, because that's what we do in the bigger course. But that's what you can do with this stuff. Now, as with the 2 sigma, there's all sorts of rules to make it, exact. There's some kind of rules with power spectrum as well, which we tend to ignore. But again, they're here, but the point is, it's good enough. It's close enough. Are we perfect? No. Are we close enough? For sure. So, although there are some of these rules, like this thing about given data set repeats forever in both directions, well, we don't want to stay on site that long, so that's never followed. But it's close enough. This one here about drift up and down, that's an important one, though, that we sort of have to follow, because if we don't follow it, and the best way to talk about that, what happens if it drifts up or down, is to go back to this step change and what it looks like in a power spectrum. Let's pretend that green step change is a drift. It's not a drift, it's a step change. But let's say it's an up or a down. What does that look like in the power spectrum? Well, what it looks like, remember I said that someone might call the green step change a sine wave with an infinitely long period. Well, what it looks like in the power spectrum is a situation where you have a huge amount of variability with a really, really big period, or a really, really long period. So just by looking at the shapes in the power spectrum, certain shapes will catch your eye and say, okay, wait a minute, that doesn't look right, or something's going on. A place where I see this catching, or not catching, but the place where I see it is if you have profiles that aren't flat and they have smiles or frowns in them. When you have a profile that has a smile or a frown in it, and you do a power spectrum on that profile, you're guaranteed to get a spike out on the left side here, which coincidentally enough might be something related to the width of the machine. And yeah, it's real in the sense that, yeah, it really is there, but it's, why it's there. Like I'm trying to distinguish between a spike that you can explain away obviously versus one that like, oh, look at that, that's interesting, we can fix that. I'm not saying you couldn't fix this one too. Maybe the profile's got that shape, and if you put the control on, you'd flatten it out. But let's say it's on purpose has that shape for runnability issues in the machine. You got to be careful now, because you don't want to go into it saying, oh, look at that huge spike, I can fix that and flatten the profile out and reduce your 2 sigma by X. Well, you could, mathematically, theoretically, but the mill doesn't want you to because they want that shape. So sometimes there's things like that go on, and that's related to that comment about don't drift up or don't drift down. If the signal's drifting up, you are going to get something that looks like a shape, and that shape will come out as a spike in the power spectrum, but is that spike significant? Or is it because of this drift or this shape thing? So that's why that one's an important one to mention and to talk about. This thing about FFT, fast Fourier transform, is a different way to calculate this power spectrum. It's a mathematical thing. We can do it in the tool. I don't think it's so important in the modern world, because all it does is it saves you about 8 milliseconds in how fast the computer calculates the values. back 25 years ago, it probably saved you 5 minutes. But today, I know it's a few milliseconds faster, I've noticed, but I don't really care.
As Dave will know, it's still important in today's world when you're dealing with big data.
Yeah, that's true, because big data takes a bit of time to crunch. And so, but we don't go into that because that's something we went through in the course.
Right.
And we did the difference between them, and you see what's faster, what's slower. But anyway. Another thing you can do with the power spectrum is create what's called a cumulative sum or a cumulative form graph from a power spectrum. Again, the tools do this for you. So it's not like you really have to do much to create this other than push a button or pick a menu option. But what this information is it's integrating the area under the curve of the power spectrum, scaling it to 100% and plotting it. So it always ends up at 100%, and that's because we've defined it that way. We like to see it go to 100%. It starts at 0. And it shows, if you will, for lack of a better way to say it, the development of the variability across the frequencies from no variability to all variability. I know it's a mouthful. I haven't found a better way to explain that. But if we look at this line here, this vertical line that I have drawn here on 40, let us assume that this is this cutoff point. This happens to be one, if you notice the axis, it happens to be an MD one because the axis is in seconds, not in inches or centimeters, which is what you would expect from a CD. But it doesn't matter. You can ignore the axis for now. Look at the 40. So 40 is our cutoff point. So remember I said before, we can get rid of everything to the left of the 40, which is the low frequency, the wide streaks, the slow things if we're talking MD. We cannot get rid of the stuff to the right of the 40. High frequency, fast things, narrow streaks. So 40 is our cutoff point. Well, what's kind of nice about this cumulative sum is you can mark it at 40, which is your cutoff, and you can read the value of the cumulative. How do I do that? We can read the value of the cumulative sum off at the 40 cutoff. And in this case, we get, I don't know, 51%, let's say. So what we're saying is, in theoretical terms, if everything is perfect, if your analysis was perfect, if your tuning is perfect, if your data is going to be exactly the same way you tuned it as it was today, which we know it's not the case, but let us say theoretically, at that cutoff point, you could remove 50% of the variability from your signal, and that's where you're going to get this reduction into sigma. That's where this 50% reduction comes from, is an exercise like this. Now, we've never put 50% in the quote or in the guarantee because we know that's a theoretical number. We know that there's issues beyond our control. We know that maybe it's not tuned perfectly. Maybe we caught a good day in the mill or a bad day in the mill. You don't know. So we typically tend to downplay that a bit. Now, having said that, I know in the past we've done this, and Chuck and maybe Lee can argue over whether they would ever do this now, is, you go in there and you say, yeah, I understand my guy told me he gets 50 theoretically, so I think a safe number to put is 35. You go put 35 in the quote, and the mill calls you back and says, that's interesting because you're exactly the same as Measurex, except Measurex promised 60%. Can you guys do that? Yeah, right away. We'll promise 70. I don't know if you do that anymore. I hope not, but we used to. Sometimes the you're making a face. Sometimes competitive pressure forced us to match what the competitor would say. So we might have been coerced into agreeing to a guarantee level that perhaps we knew was not so realistic or very, very difficult to achieve. Hopefully we don't do that anymore, but you never know.
What we
On
the CD, what we have.
Well, CD, MD doesn't matter.
Well, but on the CD, what we've gotten to is like, if we know that we're talking about a 60 millimeter zone, right?
Yeah, we can estimate a response.
We know what our response is.
Yeah.
We have an idea what theirs is, and then we try to educate the customer.
Right. If you can educate the customer and explain why 60 is not realistic,
right?
That's good.
Why 60 millimeter? Why you really can't? That's almost
Reduce
where
it by 60%.
I almost think that our report should get away from showing the zone width to the effective zone width.
Well, it does. That 40 is really not the zone width. That 40 is what determines the capability that Dave was talking about, process capability, is the x-axis. And that is determined by the width of the response. Actually,
I know what you're saying, but I think that we've historically used the zone width in our reports, and I don't know, Dave, have we changed that, and have we gone over to?
No, well, the thing is that we always say when we do, let's say, an analysis for a steam box, for instance, we say the response with, we
Click
say,
OK.
if you choose, say, a 60, 80, 100, 150 spacing, this is what we should expect
Yeah. And
from us.
yeah. And I know in the course, in the full 3-day
It's just a
course,
matter of making
I
sure
have an
we-
exercise where I do exactly that.
It's
Where
from
I,
us. We can't, like, this is not a generality,
no,
but it's what
it's
we
what
can
we do, or what we can do.
with our
Yeah.
Unfortunately, the issue is a little bit more complicated because the response, it's not the response with either.
No.
It is really the response, it is the Fourier transform, that term that he used, of the response that determines that point, which is related to the shape as well.
Right.
But I mean, there are some simplified rules.
Right.
We
But-
just need to know how to present that.
Right,
Exactly.
That's where it gets
And
but
that's why you never quote that number 51 or whatever that got there.
well, there's
Well,
two
let's
sides.
also assume the power spectrum used at 51, you're also assuming that you have infinite control capability.
Right, which you may
Right.
not.
And that's where
You
the
may not be if you've got a very strong shape.
but
very
this is
extreme,
where, like,
shape, your profile.
somebody like Apostolos is going to know with Weyerhaeuser, right, or with IP.
Yeah.
So he's got the background, he's got the knowledge to understand and to be able to sort through this.
Right.
But
So
I
if
think
you're presenting this to him,
I don't think that we have always done what we need to do to educate our customers so that they can peel away, pull the curtain back.
I agree. I mean, like, what Dave said also. Somebody like Apostolos will catch that. What you just said. Well, no, you didn't use the right words there. You said infinite process capability. This doesn't assume infinite process capability. This assumes the process capability of the actual process you're doing. That 40 is process capability, period. It's not infinite. It's not. It is capability of that process. But can you do it?
actuator, infinite actuator,
Yeah.
or actuator, yeah.
So you have to use the right. Apostles will catch all of these.
Right,
Yeah,
but
and that's just it. If
here-
you're presenting
can-
this to him, if you're presenting this to him, you better have Steve Bale there. You
Here's-
better not just do this on your own.
I'm getting worried. I think
Okay.
they have.
Or, you know what I mean? Like, you need, again, it goes to your place, to your audience. Okay, if you're presenting this to
I
other
think we
people.
need,
What-
we need to be sensitive about it.
Here, what I'd like to see is that let's, if we can take one of the takeaways from here is let's look at what we currently present our customers on our CD profilers, and then I'm pretty doggone sure that what we're showing is the width of the profiler as opposed to the effective response width of the.
What we show typically is,
I'll bring them up
something
and show
like a
them.
2
They do.
sigma of a zone resolution profile less than X. Maybe
And
real
this is
average
not
or-
a get
or something.
Dave or anything. It's
Let's
like
face it, we
this is a
struggle with this
this is a
concept.
practice. This is a practice that we've used for 6 or 8 years or however long, and I know what I've shown the customer. I know what I've done to try and educate them, and I need some review on this, so that we don't send something to the customer that they're going to put beside the other guys and say for us.
Why is it different?
Because
Or-
we know that our 80 millimeter is better than anybody's 40 millimeter.
We actually hope that we can send a written document. I mean, do we try to win these with a written document?
No, of course not. But you lose a little bit of control once you leave it there.
Well, yeah.
So if the document is not clearly structured so that the explanation is obvious, it makes the task of whoever you leave it with more difficult.
Like what Dave said about the different actuator spacings, that's one of the exercises we do in the 3-day course, is we give an example to the students and say, if the actuator spacing is X, calculate the cutoff point. And then we say, well, if the mill was considering buying Y actuator spacing with X, would that make a difference? How much would that improve their guarantee? Is it worth their trouble? Actually, the question I specifically asked is it worth it for them to buy the narrower actuator spacing compared to the wider? And so everyone goes through and it's an interesting question because everyone goes through the calculation and the wider spacing gives them a 50% reduction and the narrower gives them a 60%. So then my question then says, is it worth them to buy the narrower? And I'm very interested to read the answers I get. Because the answer I want
depends on the ROI.
Yeah, the answers I want is it depends on the ROI. It depends on how much money we're going to charge them for the extra spacing. It depends on, but it's interesting to see the answers because some of them say things like, oh yeah, for sure it's worth it. It's 10% better, no brainer. And others say, oh, 10% is nothing. I wouldn't bother. I'd buy the cheaper one.
It's better for us because we get more money.
Yeah, I know. Or anyway, it's a sideline, but it's interesting to get people thinking this way. And what you said, Chuck, about the guarantees is the whole reason for why this is, I think, an important thing, at least for sales to attend to, for project managers, for service managers. And even I was talking with Seyhan about this, that the next time we do one of these meetings, I want to do this thing again to catch the rest of the people who weren't able to stay today or weren't even able to make it to the meeting. Because there's still at least 7 or 8 people that I can think of who either have not stayed or couldn't even come to the meeting that should be here.
Should it be optional?
Well, that's what Seyhan said. That, maybe for certain people it can be optional. Like for I don't know. You know what I mean? Like for some people it can be optional.
I want to go out on a limb here and say that customers' expectations are, even if I'm right, they're not going to accept this from the sales. That's why I said
They may not accept this from a salesman.
I could never educate a hospital. I never could. I know I could.
And that's
Even if I
all
was
right.
right, because he wouldn't take it from me.
That's
I have
all
to
right.
have
Steve,
Seyhan or
yeah,
Steve.
well, and sometimes that's
And
true.
that's what we should plan on. We should never leave a sales guy.
No,
With
I
that's his
agree.
sword.
Hospitals is a different story,
yeah.
but I think.
But not every mill has one.
Well, every mill has one, but they're not as smart as the hospital.
Yeah. Yeah. Okay,
Everyone
yeah.
used to have one. Every mill used to have one.
Yeah. I mean, I know I've been on sales campaigns with salesmen having to explain this stuff to customers. And other places, I've been on sales campaigns helping salesmen, and they looked at the number and said, oh, 20% improvement to Sigma, okay, thanks, bye. They couldn't care less about how we got 20 or what 20 means, or couldn't care less. They were more concerned with how big the scanner was or something, And other places, all they cared about was, how'd you get 20 here? What does it mean? So everybody's different.
My concern is that they'll build a KT analysis, and they'll go through their analysis process, and if the category that they put in the KT analysis isn't massaged to incorporate the response width, then they'll make a decision that the other guy's 60 millimeter is equal to our 60 millimeter, and that's all that's in there.
That's the problem with KT analysis.
Agreed.
Because they're junk unless every category is independent of the other, and nobody has ever done it.
I know. I agreed. Agreed.
Very fun to masturbate.
Yeah, and this course really is exactly that. Awareness.
Because it's all men.
Yeah.
And we may have some.
Yeah, there'll be that's the last part of the course. There's slides on that
That's
later.
after 6.
And there's slides on that at the end.
Looking around.
Music comes on.
Yeah, that's a little later. So here's another interesting thing to talk briefly about averaging and filtering. I've got 3 signals up there. I've got a really pale green one that's hard to see. I've got a red sine wave, and I've got a brownish kind of stepped version of the sine wave. Okay, the brown step version is an average of 5 values. The red sine wave is a filter with a wavelength of 10, and the green is a signal. And sometimes you filter, sometimes you average. That's fine. But when we go down to the power spectra of those 3 signals, we see different things happening to the power spectrum because of what we've done to the raw signal. So the raw signal, let's assume for a second that the raw signal is the truth. Having said that, the raw signal may not be the truth, but let us assume that it is the truth. So that pale green is the reality of the process that we're looking at right now. And the power spectrum is what it is. When we start to do things like average and filter, what are averaging and filtering doing? They're taking away the highs and they're taking away the lows. They're reducing the 2 sigma. If you calculated the 2 sigma of this green graph and compared it to the 2 sigma of the brown and the red ones, the brown and the red would have a lower 2 sigma.
Jay, you can make a perfect analogy to a paper maker that they do understand here. It's equivalent to changing the level in the machine chips. It's the same differential equations. And they lower and high pass, they're low pass filters.
Yeah,
that's right.
And that they will understand that, so that can help you explain what you're trying to show them.
I never thought about that. So when we look at the power spectrum, okay, so we can understand that about how the 2 sigma number is going to change because of our actions in filtering or our actions in averaging. That's fine. We understand visually what the graph will look like, how the graph is going to look different. Fine. Then when we go down to the power spectrum, what we see is the parts of the power spectrum that have big wavelengths, again, I don't know if this is a profile or if this is an ND trend, I don't really care. It's a data set. So that's why I didn't say, periods or seconds. I called it just big wavelengths in the power spectrum. These big wavelengths are preserved. Doesn't matter how, in this case, doesn't matter that we averaged it or we filtered it. The variability at the big wavelength end, at the left end here, is preserved. It looks the same on all three graphs. Where things start to look different is we go to narrower variability, or smaller variability, I guess I should say, in the graph, higher frequency, narrower, faster, if I use all the words. That's when the graphs start looking different. Because what we're doing in this filtering and this averaging is we're removing components of a higher frequency from the signal. So the averaged or the filtered version of the signal doesn't have these high frequency components in them.
Can't help being easier, but it does become, the distribution does become more normal.
Yeah. And if you filter it enough, it'll become flat. So we have to, and this all completely plays back into which basis weight has a 2 sigma of 20. Is it the raw basis weight, the one where you filtered it, the one where it's an average? If anyone looks at a scan average trend of a variable, it tends to look like this brown steppy one. It goes in steps because a scan average comes in, let's say, once every 30 seconds. What's a scan average? Well, scan average is the average of the scan. If you plot a scan average basis weight next to, let's say, 1 second instantaneous data basis weight or 5 second instantaneous data, you'll see differences. The faster data, the 1 second data will tend to look like the green line, and the scan averages will tend to look like that brownish line. And so the scan average 2 sigma will be less than the 2 sigma of the 1 second data. And that's fine if you understand it and you realize why it's less and what it's doing. Now, we want to do averaging sometimes. I'm not suggesting we should never do averaging, because averaging has a purpose. This is one of the purposes of averaging, right? Reducing signals that we don't want to see. We think of any signal that we sample, there's some kind of target signal that we're trying to measure. There is some other periodic signal mixed in with our target, and then there's some random noise. If we do insufficient averaging, what ends up happening is the target is preserved, and these other components are reduced. They may not totally be removed, but they are reduced, so we can get a better visual look of what the data really is for the target we're trying to measure. So averaging is a good thing to do. Don't over-average, obviously, but you have to understand what you're doing when you average. And again, like I said before with the data, I'm going to say this probably 5 more times. Don't use that data to come up with your guarantee and then prove it with this data, or vice versa. Compare apples to apples. Understand what you're doing to the data. Now, this thing relates into the concept of aliasing. And the idea that, and again, I wish I had a blackboard to draw this, but the idea that if you try to sample a signal that has variability in it, and you don't sample fast enough, the signal you get as a result will not represent the actual signal that there is. You will have aliased the signal. And there's a sampling theory that says that you cannot correctly measure variations with periods less than 2 times the sampling interval. And as I say, when I draw this on the board, what I do is I draw a sine wave on the board and draw a bunch of x's on the sine wave representing my discrete samples. And I draw a couple of sets of x's. And some of the x's, if they're close enough to each other, do a pretty good job of exactly matching the sine wave. And other x's, if they're far enough apart, it looks nothing like the sine
Can
wave.
I tell you what I think is even more effective? Show a picture of an old movie where the wagon wheels are spinning back.
Oh, because of the flickering of the camera. Yeah.
Either that, or you just use using sampling. You sample at 44 kilohertz because your hearing gears up to 22. You double the highest frequency.
So that
Well, I mean, that's
so
for
that
people
you
to understand
have it
what
properly.
aliasing is, because we perceive it, well, the wheels can't be going backwards. That's
Right.
what aliasing is.
Yeah. That's a good way of doing it. Anyway, I always do it by drawing the sine wave on the board.
I'm always trying to find simpler ways.
Yeah.
Even though I like doing
I
it.
thought you had a chart that showed examples of that.
That one I always draw on the board, the sine wave.
He doesn't want that to get into competitive.
Yeah, that's those X things are pretty secretive. And again, here is one example of an aliased and a an anti-aliased signal, and then a non-anti-aliased signal. In other words, a signal with aliasing and a signal without of a bunch of this data. And so the real data is that purpley, noisy line in the middle, and these are all the pieces that make it up. And you might recognize those pieces from my other power spectrum graph. But anyway, the point I want to make here is that you see when you compare the two signals that there are times when they're essentially the same. There are other times when they are just slightly different, and then there are other times when they are very different. And the problem with aliasing is that when you have an alias situation, all you have is the alias signal. You don't have that before signal, so you can't compare them. You think that the one you have is the truth, but the truth is really the other one. And so you're performing control based on the red signal, whereas in reality the process is the green signal. So sometimes the control works, sometimes it looks stupid, sometimes it's not so bad.
This happens in
etc.
frequent plants too.
It happens everywhere, I think.
Anyway,
It can happen everywhere.
Well, actually, it's because of time lags in the process. You can compare them in real time. One's
Again,
still-
anywhere you have digital signal where
Yeah, you can have this happen.
Yeah.
And here it is in a power spectrum. So what's happening is you're because of the aliasing situation, you're losing this peak, this 10.39 peak, out of your power spectrum. So your signal is losing that variability, and so therefore it's a different signal. And so your control will never be fixing that 10.39 because it's never even going to see the 10.39 because it's going to use the other signal. So
Don't you mean that the 10.89
or 8.9, whatever. Now,
actually not a real peak? That's
Yeah.
from the not anti.
Yeah. Yeah.
So that's a false.
So that's a false
That's
peak.
it, yeah.
Okay.
You don't
It's
want
You said the
sometimes-
other
Oh, sorry. Yeah, that's a false peak.
I'm paying attention.
Well, that's good.
You're
That's a
very
false
good, yeah.
peak.
You know, it's sometimes called ghost frequency.
Yeah,
That's
yeah.
what it
Yeah.
is.
I
And
am
again,
paying
as I
attention.
say, you don't know that it's fake because you don't have the two to compare.
Sure.
You only have the one with that peak, and you react to that peak, but the peak's not there, and you do the wrong thing. Sometimes, but not always, right? When you're reacting to those peaks at, not wearing my glasses, I can't see, 24.5 and 98, when you react to those peaks, you do the right thing, because those are really there, and that's fine. But when you react to the red one, you're doing the wrong thing. Because really, that's some kind of super high frequency peak that got misrepresented in the sampling. Now, here is some place where this can catch us. It's very easy to go to a mill and say, I need to do a process analysis to come up with a guarantee. Do you have any data? And they go, oh, I've got pi data going back 1,000 years. I'll give you some pi data. So they give you some pi data, okay? And then you go take it and do your analysis. That's all fine and well except for one thing. So who cares what their system is? They have a system, they have I/O cards, maybe there's some filtering, there's a loop. They have a historian, their pi system, okay? Is their pi system actually collecting data from their process at a certain interval? It probably is. Do you know what that interval is? Maybe you do, maybe you don't. Is that interval constant? Maybe it is, maybe it isn't.
It's worse than that.
Is pi doing compression?
There's client and server parts, and there's client side filtering or client side averaging.
And you probably don't know what it is.
And
You don't
there's
know.
also reporting by.
My exception.
Yeah.
That's
So you don't
the
know.
killer.
And so again, you use that data to make a guarantee. You got a number, looks good, right? The math works, you got an
Our
answer.
engineers have struggled really hard with NTech stuff and what's that, the loop sleuth stuff, because they had no clue that there were certain, basically their historian, it was a low pass filter.
Yeah, and you were starting with data that was not accurate.
Antec never accepted data from pi like that.
Yeah, and we can get caught by this very easily if we're not aware of it and we're not thinking about it and we're not understanding this. It's very easy to get caught. Because a lot of places have historians and they're more than willing to give you all their historian data. But the question is, can you actually use it for anything? Yeah,
So how do you confirm whether that data is valid?
Well, you have to
You can
ask
actually do
this
a
question.
Fourier analysis and see that there are no frequencies below a certain line.
Yeah, that's one thing you could do and say, wow, isn't that coincidental? Or you have to ask the question. You have to try to get an understanding of how is that data collected? How is it stored? Is it compressed? Is it by exception?
The problem
Is
is
it...
they don't know.
They may not
want
know,
their
yeah.
black box,
Well, some
especially
do,
to the
some
user.
don't.
And you know what? If they don't know and you don't know, then you
Bad
can't use it.
situation.
You don't know.
But let me say this, IP nodes, for example.
It's, yeah,
Because IP
probably true.
has a good system where they collect data from all their mills, and they turn off the when they need analysis. And I don't know when they do it or if it's on all systems, but they know when they need analysis data, they always turn these features off, filtering, etc. So they use the data. They know exactly how it's collected, and that it's empty and it's.
And you need to know if you're going to use it. That's why I mentioned this.
Good to know.
So, I mean, I think I've said this. When can aliasing hurt you? Well, actually, this is an interesting point. When can aliasing hurt you? Quick samples taken when the actual process change is much faster than the sampling period, right? Think of my sine wave with the x's. Well, what's something we do all the time where we're taking snap samples of a process that's changing far faster than we are sampling?
So it's changing like this, and we're going
And we're sampling
snap,
once,
snap.
yeah, and then, yeah, and we miss all the detail. It all changed. Okay, so what's a process that we do all the time that we do that to? Right there.
Oh, yeah.
Lab tests. Right? Isn't that what's going to you run a whole reel of paper and you pull one sample every hour or a couple of samples every hour and say, oh yeah, the lab is right. The sensor has no clue what the truth is. The lab is right.
Yeah,
you need to match the lab.
Come to us and say, well, your profile is no good.
Exactly. The lab is right because
Yeah.
we just sampled it. That's the, you know. But again,
I did several times.
you know, anyone who's
I did several times doing lab sensor correlation, and there's something sinusoidal on the machine.
yeah, and we see it in our profile or system.
Might be inconsistency.
Yeah.
Control is sinusoidal, and the whole machine going up and down, and you have to catch 5 high spots.
Yeah, and they say it's perfect. It's flat. Your system doesn't know what it's talking about. There's no sine wave here. So again, you need to understand. Okay, you need to be aware of it. You need to watch out for it. That's why I mention it. You need to use the information from more than one data point to make decisions. I always say to people, I only need one point to draw a straight line. I can draw you any straight line with one point. It might not be the right one, but for sure I can draw you a straight line with one point. So you need to get information from more points. Now, what's autocorrelation? Well, autocorrelation.
Answer something before you go on, because this is really important. And you've heard me say this in front of a customer, and sometimes I got some comments about it. I always say scanner data always lies to you. And the aliasing is the reason for that. All scanned data is aliased with MD variability. There is no exception.
I think I have a slide on that.
Oh, you do? Okay.
Okay.
All right. I think it's very important.
I have a slide on that.
Hang on, let me finish.
It's okay, though, you can say it.
It's important because of IQ Select. What Select is doing. So, you take it.
Yeah, but anyway, I have a slide on that.
Then you can measure that and get rid of it.
Okay, so autocorrelation. Here's another thing where it's too bad we don't have a camera for the people who are remote. But an autocorrelation is when you take a data set, everybody here can see me holding up my hand, and you correlate it to itself, and I'm putting my two hands together, that's a correlation coefficient of 1 because the data matches itself.
Perfect.
Then you correlate the data to itself as you shift in time. And as I'm shifting my hands relative to each other, sometimes my fingers line up with each other and the correlation is pretty good. Other times my fingers are between the spaces of my other hand and the correlation is very poor. And so what happens from this autocorrelation is you take a data set, you correlate it to itself, starts at a value of 1, they always start at a value of 1, and you shift it in time. Any data that's cyclic will have a repeating, oscillating type of autocorrelation like you see with the red graph. Any data that is random, like noise, will tend to look at that dark blue graph where, obviously it starts at 1 because they always start at 1. But then as you shift it in time, it's never going to predict its own future because it's random.
Right.
So the correlation is going to very quickly get to 0 and kind of bop around 0 and stay there. The pale blue line, which is very hard to see, that pale blue line is our step change. But anyway, the point I'm making here with the autocorrelation is that quote-unquote perfect control, as I say, should only leave random or uncontrollable variability. And so if the control is well-tuned, you would hope or expect that the autocorrelation would look like the dark blue one, not like the red one. If you have a control, so this goes back to this, my 2 sigmas 1.41, I met the guarantee, but I never looked at the data to see what it really looks like.
Right.
Well, if you were to do an autocorrelation on that data, if it looked like the blue graph, then you're good. If it looks like the red graph, what's happening is you've tuned your control, you meet the guarantee, but you're oscillating down to 0. So yeah, the control's tuned, but it's not very well tuned. Of course, you can have the opposite situation where the autocorrelation oscillates at a constant rate, or close to constant. That means you're not even fixing it. Or it gets bigger. That means a disaster is about to happen, but you probably would have noticed that already. But anyway, that's the value in autocorrelation. Another quick and easy way to tell is the control well tuned. You can walk into a mill, you can collect your scan average data, because that's what we tune. RMD control scan average. Collect a bunch of scan average data, run it in the autocorrelation, press the button, boom, there's your graph. What does it look like? Does it look like the red line or does it look like the blue line? If it looks like the red line, you've got some work to do. If it looks like the blue line, you might be okay. Now, having said that, one other thing to mention about that is, in this particular example, you can see how quickly the blue line goes to 0. The speed with which the variability gets to 0 is important to consider as well. If this blue graph looked in such a way that it still went to 0, but instead of going to 0 at, let's say, 5 or wherever it goes to 0, let's say it went to 0 at 80, then you can argue, well, the control's not oscillating, because if it was oscillating, it would look like red. We're getting to set point, and 2 sigma's probably okay, but it's taken an awfully long time to get there. It's really slow and sluggish. Is that a good job? Probably not. So you can, again, just by looking at this very quickly, get an idea, like go, no-go kind of analysis of things and say, it's good, it's bad, it's half good, it's
I wonder how many of our QCS
None.
engineers are doing this.
None. I tell them about this in the applications course.
And this would be something
Quick and
valuable
dirty.
to put in a report.
Quick and,
Well,
only put it in a report if people understand what it is.
You're trying to control MD and CD at the same time, and they interact, and it wouldn't look really good.
Okay.
It may not. And anyway,
Yeah, but
and this is
I've never
a
heard
time.
one
This is a
engineer-
time. This is an envy
But
thing.
you
I've
can
never had
do
one
the
engineer
data
tell me that
fixed points
I
and
tuned it, it looks
makes
good, but
sense.
the autocorrelation doesn't, or does.
It's too slow, or
Yeah.
it's oscillating down.
Hey,
Sometimes
Dave,
you see
you know
the
that?
oscillating down if you look at a trend and you watch the trends of the loops. You see it's like going down to set point, and it's going to set point, but it's oscillating its way to set point. And if you notice that, if you take the time to look, you'll say, "Oh, that's not good." You know.
But the thing is, Jay, and keep this in mind, George, if you just simply plot the trend data,
You'll
you'll
see
see
it.
the set point change,
Right.
you'll see the exact
Yeah,
same information, and it's much more visually intuitive.
I know. That's why I said I don't use this very much because, yeah, it's kind of like a parlor trick.
Yeah, I know how to
You know,
see
okay,
it.
it's
I'll say
cool,
control
but
without this.
yeah, it's easier to look at a trend. And like I said, you take the time to look at the trend, you'll see it oscillating down.
Yeah.
Okay, or you'll see how long it takes to get to set point. You'll say, wow, that took a long time to get to set
It's too
point.
slow.
Yeah, but anyway, the point is you got to look.
Right.
And you say, how many guys look? They don't. They do their tuning. They calculate it to sigma. And if it's below the limit, they say, I'm done. Bye.
They take the number off the real report.
They take the number off the real report.
Yeah.
Yeah.
And if there's a set point change, throw that one away.
If they notice the set point.
Well, actually, the school does.
Yeah, if they notice it.
You know what your competitors do? They just stop scanning near the edge.
Yes.
Yeah.
Yes.
All those edges are a hassle.
We
We
would
need to get
never
rid of
do
them.
that. No, we've never done that.
Anyway, the whole point of this course and these topics are to be aware of them and to think about them.
Uh-huh.
I'm not saying you do everything all the time, but once in a while it doesn't hurt to do this periodically. And like I've even told people in the applications course who've taken it, I said, you know what, when you go back to the mill or the next project you go on, just run a few of these just to see what you get for fun. I don't know what you're going to get. I don't care what you get. I just want you to go through the motions and understand what's come of it. And like, for example, Johan. Where's Johan? There he is. He was sitting over there before. Okay, Johan wants John Rice to go and maybe do this kind of stuff on some existing mills so you get a feel for, are we in good shape or are we not in good shape? Maybe if we're not in good shape, we could come up with a case to go to the customer to say, you know, your tuning is pretty poor. How about you let us come in and we'll tune it up for you? So there's ways you can use this information.
I've seen plenty of examples where I know the tuning is poor, but I never had any benchmarking. You know what I mean? I don't know how poor it is
Yeah, I mean-
relative to how well, how good it could be.
Okay, the other way to tell it's poor from a power spectrum, for example, is go back, let's say our cutoff is around, let's pretend that this 10.89 is really there, and our cutoff is 10.89. a control that's well tuned theoretically should be able to get rid of everything bigger than 10.89.
That's the important part about what's the cutoff.
Well, we'll get to how to get the cutoff, okay? Not at the point where I'm telling you how to get the cutoff, but
Everything's got a qualifier here.
Oh,
yeah. Well, but all this stuff is like that.
What
So
do we have
the
to
thing
do?
is, if you did a power spectrum of a well-tuned control, you would expect that everything to the left of the cutoff is close to zero.
Sure.
If it's a poorly tuned control, then there'll be stuff to the left of the cutoff. So that's another way to tell, is your control tuned? I mean, yeah, it's an auto, the guys use it, but is it doing a good job or not? I don't know. We'll do this. You'll tell right away. And because we have tools to do this, it is very easy to do this. You don't even have to understand what this means to do it. Okay, it's that easy to do. Oh, sorry. Cross correlation. We'll have a break in a couple of minutes because it's just about an hour or so into this.
Okay.
Cross correlation is the same idea as autocorrelation, except that you're comparing one variable to another, looking for relationships. Now, my favorite example of cross correlation is stock flow and basis weight.
Yep.
If you had no idea they were related, you might cross correlate stock flow to basis weight, and you might discover by some bizarre coincidence that after some time after you change your stock flow, basis weight changes too.
Right.
And the correlation's really good. It's a positive correlation. Stock flow
And they're
goes
just
up,
out of
basis
phase
weight.
by some.
It's out of phase by some amount of time.
Right.
And that amount of time would be related to the dead time on the paper machine.
Exactly.
So that'd be an interesting experiment to do to see if it really is true. That's the idea behind this cross correlation.
Yeah.
So if you start doing it to variables that you don't have a good understanding of, you can use it to find interactions.
Yeah.
And that's the purpose of it, or that's how we would like to use
That's
it.
even how the frequency analysis works.
Yeah.
Where you're looking for rotating speeds and the
Yeah.
correlation between that.
And then a spike down the IQ Select tools.
Yeah.
This is from Plant Triage, which I tossed in the course when we had Plant Triage. I guess we don't have Plant Triage anymore, which is too bad because this was a really cool thing. This is a whole mess of cross correlations done very quickly, presented by color, like false color display, if you will, where you have all these variables down the side here and one variable, which I can't read without my glasses, across the top, and you're cross-correlating
And where
all
it's
of
red,
those.
they correlate.
And where it's red, they positively correlate strongly. Where it's dark blue, they negatively correlate strongly. And when it's this yellowy, greeny color, there's no correlation. Yes.
When you say
Oh.
negatively correlate strongly,
Okay,
that means
means-
they're 180 degrees out of phase?
Means opposite direction.
Right.
Yeah.
They're 180
Yeah.
degrees out of phase.
Yeah, exactly. So like moisture.
Magnitudes are similar.
Yeah, but not necessarily similar, but they have a strong correlation. But as one goes up, the other goes down.
Yeah, it's
So like
180
moisture
degrees.
and steam pressure
Yeah.
would have a negative
Yeah.
correlation.
Yeah.
Stock flow and basis weight has a positive correlation. But they can be strong.
But
or
they
weak
are
correlated.
correlated.
They correlate.
Just a matter of the impact.
Yeah. Question from the back there.
We just try and do it.
Yes,
Like,
there is.
you
Yeah.
strip one profile per variable.
For sure. We have tools. We have tools to do this. If we have Excel-based macros, we have profile analysis tool, we have trend tool. I don't want to get into the tools on how to do this because that's the tools course. That's a 3-day course I teach. But anyway, there are tools to do this. It's easy to do.
It's another revenue stream.
It's easy to do. So this is a good time to take a break for maybe, let's say 10 minutes.
7.3.
7.3 minutes.
But what if my watch only steps in 10-minute increments?
Well, it'll be maybe a little after 5. Because there are a lot of questions and comments and discussions.
Jake, I'm sorry, but I have a new iWatch and it only steps in 10-minute increments.
I see. Value you guys. That's what I meant. Okay. The first question is how many of these reports, and then how many of those guys shot it.
Whatever they use, why you say I'm trying to schedule as the SAP.
Whether there is
Yeah. Yeah. And over to your product, and then we'll do that for you.
Okay, that's fine. That's good.
I guess, yeah. I mean, you're going back tomorrow, right?
Or is this one?
No, I'm like, but I'm like, I'm here all night tonight.
It's just, like I said,
And I could certainly explain it to you, but I don't think it's not that hard to go through the mechanics. Because you don't have to cover it. I can understand. Okay, I have the tools. Oh. Do I have that?
maybe, no, but you
That's a good question.
So,
Actually,
hey, Dick, you know how to use Mac?
How different can it be?
Well, I'm running Windows in a virtual machine, so that's what you're
okay.
looking at right here.
Oh, all right.
And I don't have my glasses. There should be.
I'm going to virtualize my
Okay,
XP machine so I can run Microsoft Money. Continue
Cool.
to run
Yeah, well,
it.
I've got that. I'm running XP 7 and you know the deal. So there you go. Have at it. Yep.
Oh no, I have them on here. I have the tools on. But I think it's fair. So it's one of the last things on the computer that I'm wondering. It is. First choice. You would do that doesn't sound okay, this is how does the actual so that's so you look at it, profile analysis,
like
same idea though with the profile. You go profile analysis, spectrum analysis. There's a process. Sorry, this is okay, and this is a one profile. Okay. You get a power spectrum. Then you put virtual profiles into one. And there's just so many. But it says you can use a spectrum. Some years later, I think that's 100%. If I wanted to see it. But so what is a bit of that is if this is your data set. So you want to average an average. Oh, you want an off and on, right? Before and after. Yes. Right. So you want an average of your before and compared to an average of your after. So that you want to, before you did this, the base does have one profile at a time. You wouldn't want to you want to and you'd export by columns. You have one big file. You could export this is your before, pull out before, and export this is your after. This is your before and after. Then you get that to them and export to Excel. The before into Excel, the after Excel. Bring it back in and run on it. And you can even use one of the tools in Excel, rotating. It doesn't matter which tool you use, but so it's not that hard. But you need to know the stats. You're not going to figure it out on your own. It's not that easy to figure it out on your own. But it's not that hard. So I get it all. That's the whole data file.
I've got a 24-hour window, but I know which hours.
There are what you want. Yeah. Now you see, for example, because you can do this. Because they're see the way I've set mouse, so I'm selecting that. There, I just selected 7 profiles out of 17. Well, or I could be a little more accurate and say, no, I meant to select 8. Okay. So there's 8 profiles. I can still look at the spectra, but now it's only a base. But it's still not an average.
Okay, now watch this one. Display spectra average from profiles 1 to 8. There's your average. So because the stability. This is the average profile and the maximum in is going down. The maximum the sigma of every point. And then the maximum in. And so the bottom one is the lower level and top of the average. That's the average. So they're in the Trinity. Yeah, great. Okay, so this is on the spectrum of your profiles that I just saw. So you have to averaging this way too, and then export this stuff. So it's not hard. You just need to know what to do. So it's a very quick and dirty way if you've got this before and after. So if you would compare them, go back to this. Okay, you can cut off. Okay, let's say that's the cut off.
No, I don't know if the cut off.
No, but no. Okay, so that's determined that from above. So you might be further cut off. And the control as well too. Because our spectrum will look like this. Before we'll look at this.
I am totally fighting with it.
Sure, but it kind of looks like it's cut off is around there because that's something that's well. You don't know if it's well.
Our main goal from this is to be able to say
Definitely
with new profiles.
I can get mine correct.
This might be your
Then you need to across the. Okay. Because what you get there is then you have a this graph, and you know where the cutoff is. That's the cutoff. You need to say, you need to plug it into the sum.
right.
You need to say.
Okay. Well, is the cutoff then our zone response?
Well, okay, so we don't have to.
No,
So
this is part of the sales process.
Okay.
Typically, I've seen reported in the past, I've seen the we'll plot the spectrum, we'll have it in
I'm sorry, where are the rounds
centimeters or millimeters or whatever it is, and then we'll take the weight, the zones with approximately to.
Well, we don't have the response.
I'm not sure. I'm not sure. I think we would. I think we do 60 millimeters. But I have to. Is it always 8.5 on that first line?
Yeah.
And then we'll go up like that. That's true. So when we go up and calculate
You need for the cutoff.
Yeah, cut off.
You would
It's
estimate 2.5 times the spacing. If we had a system that you had above this, then you get the real response. But we don't have a system. Okay. Then you estimate it.
Is it our Steve wants trying to be
We're trying to sell our response. Yeah. So you estimate it at 2.5.
So then
you have cumulative sum like I did. And you go to read the value off at that point, and that's your whatever 51% that I had on my graph. And then you have to start thinking, okay, I'm not going to tell it has to be one theoretical maximum. And you meditate on black magic and whatever, and how it's
Obviously, you're not the Ferrari group.
what I think we should do is show on this.
Let's not be. I'm sorry. No,
Hopefully by tomorrow, my cigar case.
Now we gotta go to the other stuff. Another meeting.
This zone,
I've already identified it.
that's how much you're improving. And it's going to be less.
What time are you gonna leave tomorrow? So I leave tomorrow.
Huh? I was thinking noon.
Yeah, dude.
We show our line. We never show.
What the hell is this?
Don't mess with them.
Somehow show.
Don't mess them up. Don't mess them up. I mean. Good.
Oh, so you're almost like. Okay.
Different wins, right?
Yeah.
Yeah. I mean, we can do that too.
I'm still talking.
I mean, we've done it before, right? So we got stuff.
Oh, no, yeah, verbally, I think verbally is good, but verbally.
No, but also.
No, but I mean, you can plot the power spectrum, you can point the cutoff, you can get a percentage. You can have different cutoffs based on different actuators, based on different conservative, non-conservative, whatever. So put it in a table and say, if it's, we're being conservative and we have wide actuators, it's 10%. If we're being bleeding edge, this is what you want to present. Yeah.
Pre-engineering, but that's
Yeah. Okay, let's get started, guys.
Done.
Because we're about a little bit less than halfway through, or around halfway through.
We're starting back.
Yeah, I know.
If not,
Here we're getting to my next slide, the Sayhan scanner live speed slide. Because the next one after this, or it's two after this.
you know when they're not right.
Postulus does. I bet you Postulus does.
Postulus Vergopolis. It used to be a warehouse.
That's that ancient building in Greece that you always see on the pictures with the big columns,
I
right?
hope he was dead, but then he popped up at IT. I knew him from warehouse.
He cares. And some other guys probably care too.
He's rather.
And it's obvious when you walk in.
Anyway, so we're around halfway done. So let us continue.
They know my
So
public
what does
friend.
scanning sensors see? Let's talk a little bit about that. You know, there's issues related to sensor geometry, the design of the sensor, how fast the scanner scans, the data box size or the cell size on the scanner. The diagonal path on the paper is what Sayhan said about the scanner is always lying to you. That's where that slide is. And how does that affect our controls and variability statistics? Well, here is a graph of a set of data measured in three different ways. The green line, which is very hard to see on this graph, is 1 centimeter data boxes off the scanner. The blue line, which is much more easy to see, which is almost the same as the green line, is this data run through a Tapio analyzer. And I don't really want to talk a lot about a Tapio analyzer at the moment, but suffice it to say, it's a lab-type instrument that you can put a roll of paper on and run it through, and it measures weight and caliper moisture. And what's good about it is that a lot of people, like Metso paper, Valmet paper, whatever their name is, like to use it for benchmarking, because they can run rolls on it from all sorts of mills, and they can benchmark them because it's that device.
They can run either MD or CD
Right,
strips.
they can run MD or CD strips. It'd be the equivalent of you taking a scanner in your pocket, setting it up, running the samples, and taking it away with you, going to the next place, putting it down, running your samples.
There you go.
Okay, it's considered a good benchmarking kind of standard device. Anyway, I don't need to get into it anymore. Suffice it to say that it's a little more accurate than the scanner. 3.2 millimeter measurement, so it's, the scanner is 1 centimeter, this is 3 millimeters, so it's a little bit more accurate than the scanner. The next one, these red dots, are measured in 6-inch slice zones, or 15 centimeter measurements. So we could think of this as the green scanner data being high resolution, or scanner resolution, and we could think of the red being low resolution, or perhaps actuator resolution, because typically we match our actuator resolution, we display data in the resolution of the
So
actuator.
you're missing all the higher frequency stuff. basically.
Yeah, because you can't fix, goes back to what I was saying about the cutoff.
Yeah.
It's good to know that you have 1 centimeter streaks in your sheet, but you're not going to fix 1 centimeter streaks with a 15 centimeter wide actuator.
Yep.
So you need to understand that.
Yep.
That all relates into this cutoff business.
Yep.
You'll see the 1 centimeter spikes on the power spectrum, but guess what? You're not going to fix them.
Can't get there.
But what's interesting about this is, if you visually look at the graph, once again, how the red graph compares to the blue and the green one, the red looks kind of like an average, where the blue and the green has been averaged out, like it's been averaged, so that there's the peaks are gone, the low spots are gone. What does that mean?
Unless you get unlucky enough to hit right on
Unless you get unlucky enough, yeah.
to hit.
And what does that mean to the 2 sigma? Well, let's look at the 2 sigmas of this exact same data set.
The Tapio 2 Sigma is the highest resolution. 2 Sigma is 1.398. The scanner is almost as high resolution as the Tapio, a little lower. It's 1.38 something. The 6-inch data boxes is way lower resolution than the scanner or the Tapio. Its 2 Sigma is way lower. This is what Chuck said. And many people have experienced this in sales phases, how you have an old scanner that measures low resolution, the 2 Sigma is 0.8. Install a brand new scanner that measures high resolution with way more points, all of a sudden the 2 Sigma is 1.4.
So are you saying you go through, and see, I seem to recall that theoretically those 2 sigmas should all be related by the square root of the ratio.
Yeah,
Okay.
yeah,
So,
sort of.
but do you actually create the new profiles?
We create the new profiles, yeah.
Yeah, that's true only again if it's normal.
If it's normal distribution and perfect, and I think I have a slide on that. I know I do in the course, I'm not sure if it's in the short course. But the point, the understanding here is to understand this and to be able to warn your customer of this if he doesn't understand. Now these days, I think the customers understand this a bit better than when I was in projects.
They all got burned by changing the high resolution.
Yeah, right. So they've been through it.
Well,
Now
what
they
they used
understand.
to do too is compare one gauging system 2 sigma to another.
Well, that's
gauging
another
system, and
dangerous
not-
thing
and
to
real-
do.
You know, they'd yell at the guy who
Yeah.
had more measurements.
Yeah, because you're just
Yeah,
saying obviously
We've
it's
been
worse.
down that path.
Okay.
I was mentioning.
Peter had his hand up first, Chuck.
Buddy,
Peter had his hand up first.
West Point, in Toronto for 3 days in a row.
When you say most customers have learned, I'd say in general, we have to remember that what we said at the beginning of the meeting is that most customers still run scanners every 20
Yeah, maybe you're right. So a lot haven't learned.
But the ones that have upgraded have learned.
So,
Yeah.
so maybe this points out that we'll need to pay special attention to.
Yeah, that's the point of it being here. Yes, Chuck.
What I would love to see is that all of us start to assume that our customers don't do 1,000 projects on scanners, on analyzers,
A
on
year.
controls, and that we run our business so that we leave that assumption in the back behind
Yeah,
us.
and we make sure that we explain to them properly.
Right, we have to treat them like they haven't gone through a scanner installation in 20 years, as opposed to like they did one last week.
But I think there's some danger there because I think that in my experience, and maybe even in myself, the first time you try to explain something to the expert in this area in the mill, they stop listening. They are convinced that they know more than you about this, so you kind of have to.
Yeah, you have to be careful.
Yeah.
That's true.
So what I'm talking about is, I got burned because I didn't know enough to give my customer the heads up
That this was
when they
gonna
put in a
happen.
new scanner, that they needed to go through a process of preparation in their QC and with their customers, or in how we were going to present our data with a new scanner. And all of a sudden, we turned the scanner on. We went through some headaches. We finally got the scanner running and now putting the data in, and we gave them out 2 signals here. Next thing you know, I'm getting a call, like, I got a problem. From the mill manager, from the big mill manager saying, 2 signals higher.
Of course.
Yeah. Okay.
I've experienced it
So
on many projects.
that's what, and then.
That's why I walk funny.
So what we tried to do on the next project this time, is because I've been but hard enough that I remembered it. So it's like, okay, we need to plan for this in advance. And what we ended up having to do is we actually had to fly Dave Lang out from Toronto, put a presentation together, come in and prove to the customers that we
Okay.
weren't way,
Dave Lang did that. I don't know how many times. How many times have you done it, Steve? How many times have I had to do it? A lot of us have had to do that because of this exact reason. Your 2 Sigma went up. Your system doesn't
I
work.
almost think that's fine. Wait until there's a problem. Don't get in this mess.
No.
Yeah, explain to them ahead of time.
Yeah,
Then they're
yeah.
not selling anything.
That's right.
Somebody other than me has to do that.
That's what I said about how sometimes their sales, their rejection criteria are based on these numbers, and all of a sudden everything gets rejected because it's above the number. Or you don't, yeah, or you make sure everything's actually level, or you make sure everything's the same resolution as the old system.
But for the benefit of everybody in this room, I've seen the same thing on 2 cap analyzer projects in the last 2 years, where we assumed that our customers knew how to install a cap analyzer and created post-installation problems. So that's I'm just saying, if we can remember as we go, as we're transitioning to our new culture, and picking up new habits, is like
That's the problem, that we control based on high res, unlimited
profile. Right. And that's what the startup guys leave on the display.
I know, and
the
then
operators.
that's what the operators get used to seeing.
They get used to seeing.
And they talk
Instead
in terms of
going
those
back and
numbers.
putting, actuator space.
Yeah.
But that should be something I think that, and I've been guilty of not discussing. If that's something we need to discuss in the beginning of the project.
Yeah.
Yes.
Yeah.
It has not been discussed in sales.
No.
Absolutely.
Yeah.
Must.
That's
Well,
why
it should, even if it was discussed in sales.
It should be discussed in the kickoff meeting,
Yeah,
sort of should be
that's
discussed.
really guaranteed.
We didn't emphasize.
But there are also cases where it is discussed and customer chooses to have high resolution.
Because they want to see it. They want to see it.
That's what they want. I mean, there are.
They have to understand.
But
if they ship by the Sigma,
Yeah.
there's a big
No, they need to know
Yeah,
the
they need to
difference.
know. And in those cases, they have said themselves that they didn't need to talk to their lab and they need to talk to their customers and set the expectations into the
They
right
have
place.
to come up with a correlation that our old sigma, this value is equivalent to the quality.
Okay, that's cool.
But it's easier to make us just put a different resolution profile up on the screen that does that calculation for them.
And we've done that many times. You have done it so many times.
We did
Dumb it down.
But yeah, exactly.
John Ball,
Yeah,
when we sold it to him, we said, John, the variability is going to look worse until we're going to do it the way we used to do it.
Yeah.
I'll tell
And they're fine with it, but they understand.
I think he's making us quote in this IP Rome case,
Yeah.
we have to do our analysis. All the vendors have to do it on 2-inch space.
Well, there you go. Yeah, Peter has a question.
As we discussed before, that I think a very common real threat, and in large part in the industry that's downsized in terms of resources, is this game of vendor spreadsheet comparison. And if we don't engage aggressively in this dialogue with those that are willing to meet us on the client side, then everybody gets pigeonholed kind of the same. And at the end of it, clients don't dig for details and understand the technology. They're more than happy to say everyone's virtually the same, and then it's not a technical decision. So the purchasers love it when they get that conclusion from the production team and go at them.
Go after price.
So we can't wait, because if you get there, then you're back.
And this is the same data plotted in cumulative. If we assume that that blue Tapio data was 100% of everything, or it isn't, we know it's not 100%. Because the only way to get 100% would be to have an infinitely small sample.
Yeah.
So we know it's not 100. So there's 100, but we're pretty close to 100. Well, the scanner is almost as close, but the 6-inch isn't anywhere near as close. So no matter how you look at the data, it tells you the same thing, that the lower resolution data tells you less of the story than the higher resolution data.
Yep.
This is this 2 sigma versus cell size square root of the two things over each other. This is actually a graph that Dave Lang collected from real cases. So that's why it's not a perfect curve. It's bumpy because it's not a formula. It's actually just data points. It's actual data. But it tends empirical data, but it tends to follow that curve. And of course it's limited in range because it's a data he happened to have. But anyway, we have to understand, and maybe we all understand. But again, I ask the question: if George were to ask every project engineer if they understood this, do they really understand it? I would hope the ones that have taken the applications course would understand it. But what about the other people? I don't know. Maybe not. Probably not. MD and CD variability from the 2 sigmas on the real reports. We like looking at real reports. We talk about real reports. We base guarantees on real reports. The mill likes them because they're either on the screen or they print out. And they're based on TAPI standards. And there's 2 different versions of TAPI standards. I'm not going to get into that and knows this a million times better than me because he was on a committee that developed the rules for these. And suffice it to say that we follow the standards for our calculations, which is all fine and well, but what's important to understand is leading into what Seyhan said before about how the scanner is always aliasing. The assumption from a scanner is what that green line shows. Scanner scans back and forth, it's measuring CD.
Yeah.
This is CD, this is MD.
Yeah.
That's what people like to think or like to talk about. The reality we quite often show is a graph that looks like this. He said, well, actually, the scanner is going across the sheet in a diagonal pattern. So there's a lot of MD in that CD too. It's not pure CD. And like the mill guys go, yeah, you're right. No, you're right. It's kind of going like this. I get it. Okay, that's fine. Okay. Well, I love this graph because this is more like the real truth. And what's important to understand is that is the CD. That is the MD, and the green line is the scan.
Say
So
it again?
okay.
At what speed?
Well, I mean, sure, the scanning speed matters, the width of the machine matters, the machine speed matters, but the profile is the green line, and this is CD.
It's a hell of a lot of MD.
There's no CD in that profile. It's almost all MD.
That's the point.
That's the point. Is there's so much MD in a profile. We say, oh, it's a profile, it's CD. Well, yeah, I don't know, it's a small percentage of CD, but it's a lot of MD. And again, it's an understanding. That's a great line. Profiles are contaminated with much MD.
Okay.
Okay, like say, what did you say? Did you say profiles lie to you, or scanners always lie? Is that what you said? That's a great line too to put there. Scanners always lie. Okay, we all say it's CD.
And you cannot correct it.
You can, yeah,
That's the
it's
problem.
it's life.
You cannot correct it.
You can speed up the scan speed,
Well,
right?
it was
That
my
doesn't
belief-
correct it.
No.
Oh, wait. you
Make
can-
the
you can
machine
scale it
narrower.
down.
Make the machine narrower. Slow it down and speed up the scanner.
IQ inside can.
Yes,
Yeah.
exactly.
Or
Go ahead with IQ.
or make the machine narrower, slow the machine speed down, and make the scanner faster.
Yeah.
But
That
you know
helps.
what else does? IQ select.
Yes, variable speed scanning,
That's
which
why I
I get
want
into
to
that in the full course about how when you start scanning at variable speeds, this aliasing kind of falls out because
Well, you can
peaks that
see
are
it
really
clearly
there
quantify that in the-
stay there, and ones that aren't there are not there. But I don't talk about this.
Got it. Go ahead.
So why don't we always scan one speed this way and other speed this way?
Well, that's what IQ select is.
But does this
Oh,
translate
that's
into?
Could be.
what
Is
we do.
capable of being.
Yes.
Does this
That's
translate
exactly.
into us feeling? I mean, if our customers aren't. I mean, all right. So that if we can better measure true CD variability, our CD control should perform better.
Exactly. And in fact, Steve has a, well, I showed it,
Well, then I take back everything I said, because then we do have to take a direct sales strategy and make people understand this.
Exactly.
But I'm going to go out on a limb here and say I don't think anyone has set up the CD controls with the scanner scanning variable speeds.
No, that has changed.
Has it? You think
Yeah, in
really?
fact, Joey's not here. Yeah.
Okay. Maybe some.
That has changed, but it took us 3 years
Yeah.
to bring that change because we kept saying this. Everyone said, no, you
Variable
don't
speed
need it.
scanning.
And they all will remember. He's finding out for the first time what select is.
Come on. I have
You just
installed
said,
it,
is
but-
that what select is?
No, I don't think that I have ever discussed with Mitzi said, hey, that needs to travel this speed that way, that's this way. We have been discussing about IQ select features, but not. What do you recommend? The speed this way, the speed that way.
Telling them to always.
Well, we have
that
all
they
of those things.
They've been
So what do you
used
recommend?
periodically. Yes.
Are they being used? No.
Okay, that's what I think.
You want specific. But you gotta work with the project manager.
There has to be an
Nobody knows how
understanding.
to do it.
First of all, the project manager has to even understand about this
Yeah,
before he can
Joey has been-
ask the question or make the statement. If he doesn't even know about this and the project guy doesn't know, then of course it's not going to be changed. It's going to be, everything's going to be the same as it was.
See, I thought the IQ select, this makes perfect sense to me now.
Yeah.
But I thought the IQ select was for when you had a certain specific type of problem.
Well, it can do that too.
Yeah.
You can do that too.
I understand,
Now
but I
you're
didn't
doing
realize
that.
that fundamentally we should be scanning at different speeds in each direction.
But here was our
Always.
problem. I'll summarize this thing. IQ select, nobody, this is our cultural issue that we were talking about earlier. Nobody had even the willingness to understand or learn what select is. There was always an excuse.
I'll give you.
Dave Lang has done a lot of things to get rid of that.
Here's what happened, because last year, January, on our project at Rock County, Tacoma, when we had our late January meeting and Dave Lang came out. So I'm in the control room with Dave and George, and I asked a question, and Dave was there, and Dave knows what this is. And George said, well, I don't even know what it is. So, and then,
Yeah.
And he's a senior guy.
And when did we, by the way, we introduced this.
Maybe not, but here's the outcome of that. The outcome of that was that Dave, I was there, Dave called Ollie. And Ollie said, well, that's a worldwide problem, and we're either waiting on training from the world or something else along those lines. So that was the story back then. Now it's up to us.
Just let me say this. We introduced this in 2008. Okay, so many things happen.
Right.
That's one incident. And that's what I mean by we need to change this culture.
But we did a poor job of training people on it up until
all of
up
the
until
above
a
is
year
true.
ago.
Yeah.
So I mean,
And salespeople are talking about these things for service
I know.
projects.
And then you don't turn it on.
I remember we talked about it at BioPropel. You were trying to tell me to get the IQ select guy. I said,
And you
nobody
probably
knows how to do it.
You
But he
probably
saw
gave
it.
him one of these.
I
Didn't
know.
you, Jersey? Shut up, Lee. Shut up, Lee.
So once everybody in the field
And
figures
it
out,
works.
once everybody in the
It
field
works.
figures out how to do it from a project standpoint, I would like to see more than just that one case in the German mill, where we can show what the impact is on
The before and after.
Yeah,
Some
we have
control.
actually,
The thing is, sometimes there will be an
Right.
impact,
And there may not
sometimes
always
it will
be.
not
Right. Yeah.
but we also have a few more cases than the German case. German case was done out of desperation because I had been summoned to give a paper in Germany, and I had to send somebody to get data because in our organization we weren't doing it.
But its impact is going to be a function, correct me if I'm wrong, of how much MD variability there is.
Yes, that's
But
right.
there's
Like Dave
always
said.
some MD variability.
Like what Dave said, it's not always going to make a huge
Right,
impact.
you can have a long frequency. It's not.
Right.
You're not
But in the
high
life of
frequency.
that mill, it's
Yeah,
going to make
in the
huge
life of that mill,
differences some of the time.
But
If it's
other
10% of the time, you're still drawing a lot of
And it's a
benefit.
more robust CD control, bottom line.
It is actually, we have data documentation showing CD control 2 sigma comes down without doing anything by just turning on this feature, because now it's seeing the reality. It's doing a much better job.
Any
More of the
MD
reality.
load
Yeah.
in the control system that's in that frequency band that the CD control responds to
Is a
gonna
problem.
be a problem.
Yeah.
Exactly.
So the
But
times
if-
that there's that signal coming in the MD,
Yeah.
Now, Peter's got a question.
Yeah.
Based on everything you just said, we owe it to both ourselves and our customers to make a point of going back to the selects and to live man without these features being turned on.
So Lee brought up another thing.
That's a good point, Jim.
Lee brought up another point of what can happen that can cause this problem. The MD disturbances don't only come from pre-head bumps.
belts. Anything that is periodic, and you'll see it. One thing it does. Yeah.
Well, see,
Calvin Food, 3 days we were in process, and the first day we set it up, and setting it up is a sin.
Yeah.
I wish I could tell you I was so smart. It's just easy. The hard part is going to the page, and there's the speeds. You just put it in 16, 18, 19.
You know, that's handy, and it pops out what the frequencies
Yeah,
are, and if you see
they
bumps,
gives you a ratio of each other, right?
if you see spikes in those frequencies, then you say, oh, look, that's the guy.
In one day, we just had to do a lot of tests just to build up our library, because Tuesday or Wednesday they were going down. There's a spike, corresponds to something 53 feet long.
Yeah. What's
Okay,
that?
well, think about that. So they have their shutdown, we come in Thursday, the spike is gone, they changed clothing, it was 53 feet long.
No way. We gotta write that up.
You go to a superintendent and tell him, hey, Bobby, get a load of this. Do you have anything 53 feet long? Because there's something wrong with it. You can watch it.
And Bobby's going to say, I ain't never got no complaints. I've talked to that boy. He knows. It's good. It's all good.
That was good. We need to write this one.
We need to write that one.
He actually, that's why I took that report to one of our management meetings and said, it's pretty easy to do.
I mean, we were finding, we did something similar, like when I visited Jackson, I did samples, picked away the scanner, popped out something. And it turned out they said, well, it's a roll diameter. It's a coating roll. Coating roll diameter. And he was like, do you think we should change it? I'm like, don't jump to any conclusions. It might have been like that for a very long time.
There's some art to that.
Yeah.
To that machine, I mean, it's machine monitoring. Yeah. That's what it is.
It's a mini sentinel.
Yeah.
It's almost like the runnability interface. You know,
So
to
we
set
have
up.
two sets of tools, right? One we have the spectrum analysis, which is what that is. But then the other is the anti-aliasing that comes in by having the different speeds. And I heard some now, and I just asked what he heard about it. Well, I don't believe I've seen the data that you were just talking about that shows when you turn the variable speed scanning on, you watch the CD 2 sigma improve.
Actually, I would like that data.
Take the phone call, I was gonna show it.
Yeah, that's right.
Actually, I would like that data.
It will be in the data that you will
It's
get.
in the presentation.
Presentation.
And say at the very end, that exact example.
Okay.
All right.
I want to say something though. That 53-foot long signal was easy to see in the gauging data already without IQ select, but it is so dominated by MD. And the reason I go on a limb and say that is that paper that I just sent you copies of, even Journeau, in their gauging system, found a backing roll out around on the coder, and the coder was varying plus or minus 50% within the rotation of the roll. And they found that data they could see in their high resolution scans. And of course, that was pure MD.
Well, if you have the raw data and you do SDA synchronous time average on those and put in all the lengths of the different elements, whatever they are,
I don't think they had that. He was showing how Fourier analysis on raw gauging data. They made like a super time series.
Yeah. But somebody had to make that.
It's built into
Our
us.
system
Yeah, it's built into us, exactly.
Yeah.
Yeah,
This-
I mean,
You don't need to do anything.
All you have to do is take
other
those
than watch it.
53-foot numbers into on the screen.
and you have to know something's wrong, and you have to go and set it up and do it.
take
And
a look.
Ian has a lot of data like that.
We'll talk about this in the project group. It'll happen.
Well, I'm so glad you're here.
I know, I wish-
Tim's not here, but
Yeah.
This is
We'll make
exactly
this
what
happen.
needed to happen before,
this
like
will happen.
2008.
Which is
I
why,
didn't understand it.
as far as I'm
That was obvious
concerned,
to me.
project managers
Yeah, but
need
then
to be in this.
you are
Yeah.
In this
doctor and we
course,
have to.
or this-
I'm just a
No,
smart
it
ass.
has nothing,
So, come on.
no, it has nothing to do
Anybody-
with
I
that.
think it-
It has to do
But
with,
then, wait, let me say, because of, we have been speeding us up a couple of years now that we need to implement those, and we have been,
yes.
and we
We've been implementing them.
and just we even introduced these things to meet the customer at Simpson.
Yeah,
Yeah.
after that.
And customer said that, I don't want to put any emphasis on those things now, we need to wait until we find somebody. But I have not gotten from anywhere that, hey guys, you really need to set two different speeds for the scanners.
And that's what I'm talking
And our
about.
QCS
I'm not
engineers
trying
would
to,
think if they, I'm not a QCS guy, I grasp this.
They haven't been.
George?
Why
Yeah,
would I
some
think- why would I
of
think
them have been turned on.
Maybe
Uh-huh.
they,
Yeah.
but
So this is it's not a story of it's never been used.
Yeah.
But it's never been
Look, guys,
advertised.
I'm not trying
A lot
to
of times
accuse
it's
anybody
turned on,
or,
it's not been
you know,
advertised.
as
I
an
think that even
organization,
you
you have
need to
done a
get some
very
from
cool
the
job
Thanksgiving
launching
to
this. It hasn't been
try that long.
Yes,
That's
I
fine.
use that.
And you know what, Simpson had sent your guys to the scanner course in Toronto, and I don't remember how we got talking about this, maybe through Chuck, but they paid, and I did a half-day thing on those IQ Select tools with the Simpson guys, and explained to them what you could use it for, and what this displays mean, and all the numbers and all that. So customers could use it too, and they could be interested.
Well,
Let's move on.
that's better marketing. We have to call it
Let's
something.
move on.
Yeah.
Let's
Let's
go.
Yeah. All right, so anyway, continuing on with this. Okay, this is an interesting sequence of pictures just to kind of reinforce this this aliasing thing between MD and CD, and I don't know if I need to go through it in great detail, but if we look at this picture here, we have a profile where there is no MD variability, okay, only CD.
That's just what PM1 looks like. It happens in code.
Okay, if that's true, then you see the profile, and who cares, right? If you manage to get MD variability equal to 0, good job. We don't care so much about it. It's not such a big deal. Okay, this is where we only have MD variability in the signal and no CD
And
variability.
it looks like CD.
And it looks like there's CD variability.
Oh, that's really a nice way to explain it.
Okay, imagine that. But of course, that's not really realistic either. Okay, what we want to get into are the rest of these graphs. These are graphs with MD and CD variability, or only MD at different time periods, and how the shapes change.
depending on the scanning time versus the period of the MD, and how the shapes of these apparent profiles that aren't real change.
Yeah.
Okay? Then now let's get a bit closer to the truth, where we have MD and CD variability in a sheet, and you still get these shapes.
Yeah.
Now, however, having said that, it's maybe a little convoluted to see in this picture. But
Etch-a-sketch.
yeah, but all these blue lines are individual profiles.
Right.
The thing with the red dots in the center is the
average.
average of them all.
Yep.
The average of them all kind of looks like what the CD profile really is.
Right.
Because the MD is coming and going.
Scans, we don't.
Yes, the MD comes and goes, right? And so the average enough of these profiles, it actually is the profile.
This is
Any one profile is not necessarily the truth.
But that statement is not correct either. In this particular case, it happens to better represent the reality. But you change the frequency a little?
I know, and then it falls apart again. Right. And what I like to tell people, when I tell the guys in the course, maybe I shouldn't tell you guys what I tell the guys in the course, but maybe I should, is I say to them, so we understand that any one profile that you see is not really representative of reality, right? And quite often some guy in the mill walks by, looks at a profile and makes a judgment based on that. But he's making a judgment based on one of these blue lines, and it may or may not be real. But so then what I go and tell the guys is, I said, but however, having said that, if you tune the control and you happen to catch a profile with a super low 2 sigma, take a screenshot, send it to your boss, tell him you're a genius, you deserve a raise because he won't understand this. Unfortunately, now you all understand this, so when they pull that trick on you, it's not going to work.
Just a quick question.
Yes.
So we display the actual raw scan on the screen. We only take control action.
No, we don't.
Based on an average.
Correct.
Of correct?
That's what we don't show.
We don't show the raw. We show
Well, whatever we agree to show.
Well, we show
high res, low res.
We can't show raw.
Zone resolution.
We don't typically show raw.
Right. We usually. Yeah. Okay. Anyway.
But you're right. We only take control action.
We're only showing one profile on the screen, no matter what the resolution. But we're averaging.
We're taking control action based on a certain number of profiles.
Four, like
I thought it was 4 to 5.
6 or 6 or
6,
yeah.
12.
But anyway,
right.
that's where this goes.
Yeah.
And here it is shown in slightly different way. Maybe this is a less.
One recent example.
Yeah.
Where we had 2 or 3 wavelengths, very big wavelengths, MD oscillation. Was at KC Owensboro when they did the dilution project. And if you look at the raw profile, weight or moisture, scan to scan, the shape was completely different.
Yeah. And you think about a CD, this is not a CD control course, but you think about a CD control, assuming you were to take control action based on every scan.
It'd be all over the place.
Exactly.
Yeah.
It'd be nonsense.
Yeah.
And that's why we don't do it.
Yeah, okay.
Good enough. Just purely of interest, I worked with Ian for 7 years. The reason he has all that data is but I know that ABZ and MeasureX calculate their CD control profiles in a fundamentally different way. One, they try to subtract some long-term MD average from every scan.
That's 2 sigmas. I think you're talking about. That's 2 sigmas. There's formulas for how the 2
the way they calculate the control profiles.
Well,
no, I think he was showing earlier truth happy standard.
Yeah, there's 2, and this thing about subtracting statistical noise from the numbers before reporting them, and sometimes you do, and sometimes you don't.
The residual.
Residual, it's called residual on our printouts, or short-term 2 sigma. I don't talk about this here. I talk about it in the full course, but and that's yet another reason why the numbers are different. Again, you pick up a real report, and you read what it says: real average MD2 sigma equals 1.7. Then you go to the display, to the real average display. It says real average basis weight on the top, and the 2 sigma is not 1.7. And it's like, well, how come it says it's the same number? Why are they different? Because they're not the same number. The words are kind of the same, but the number is not.
Kerry Figel of International Paper will present a paper on exactly those 2 standards and
the differences between
this coming paper. And Calvin and I actually have looked at how our data affects this IQ Select data and published a paper, I think it was 2010 or something like that. So there's a lot of information out there about that.
And this is the same thing with how the CD bump can look like a bump in the profile, but so can the MD bump. It can look like the same bump. Okay, this is this thing about constant speed scanning versus variable speed scanning, and a real life example where they had two scanners, one at the size press, one at the reel, and they set the, I've got to make sure I got to say it the right way. The blue is the variable speed scanner, and the red is the constant speed scanner. And they purposely, on this multiformer, induced an oscillation stock flow for testing purposes and watched what the scanners would see. And if you look at you can see what you can see how they purposely made the stock flow oscillate. They moved the valve, the stock flow oscillates, that's great. The bottom was left essentially constant. And then when you look down on this bottom graph with the two moisture measurements from both scanners, okay, you see the red scanner, which is the constant speed scanner, missed most of that oscillation, whereas the blue scanner, which was the variable speed scanner, saw most of it. So this is a real case of where this variable speed
But it
scanning
didn't see it in any individual scan. It has to build that relationship over several scans.
These are scan averages. These are scan averages.
That's a function of the frequencies, your oscillation, and the frequency.
Yeah, you scan it. You could miss it. You could still miss it,
Right.
depending on it. Or you could not miss it, or you could better resolve it, or you could worse resolve it.
It goes into the sample.
Yeah, right. Well, yeah, remind me. Write a note and tell you again. This is the German example. Here it is in a power spectrum. Here's the power spectrum of the data, where you see there's a spike in stock flow because we purposely did it. And then when you go to the two different scanners, you see the size press scanner, who is the variable speed, he sees the spike in the same place, so he sees a variability there. The real scanner, who is not scanning variable speed, sees a maybe you could argue he sees a little bit of variability there. Maybe that's just noise, but you can clearly see how this variable speed scanner sees more closer to the truth.
That's awesome.
His power spectrum more closely matches the reality of us fooling around with the stock flow.
Yeah.
So he sees better, closer to the truth, or he sees more truth.
So,
this is actually all in mass stock because this is a paper. This is the paper I was talking about that I gave in Germany. There's a whole presentation about it.
Okay.
What do we lose by presenting this? Do we have an intellectual property that we can protect?
We actually we have patented this.
Okay.
We have patented the variable speed. So nobody else can vary the
This
speed.
is years someone
for the war.
Yes, as a matter of fact, each of you owe me $100 for me doing this presentation because of those patent rules.
But nobody can.
But you can pay me what you
They
need.
can probably vary the speed. There are ways to get around it.
Of
That's
course.
not the point. The point is that we have intellectual property.
Yeah, but the fact that we've patented this, we can spread a little bit of FUD and make it, because there's patent indemnification issues that companies might not want to risk.
This is not it. That's right. This is not a new idea. When we were developing CD control, we knew this. It's just a matter of doing. When we were developing CD control, I was working with SCFI at that time.
The computer wasn't fast enough to make these calculations, probably.
But then we decided, how can we really do machine troubleshooting? Okay. And SCFI had a project about that, and they started changing the delay, and we had this discussion, changing the delay at the end of the scan rather than varying the speed, because scanners couldn't do it. So you can do the same thing by having a variable delay at the end of a scan, because it's all about breaking that pattern, right? So that is patented too. It depends how you write your patent.
Now this is a very just quick little overview of some of these displays and what's on them. This is one of these IQ basic applications display, and it's the basic applications, so every system gets this. Okay? And this is something that people ask me about a lot. What is this stuff in the middle here? I don't want to talk about everything here, but first of all, this thing here is just a static display that's trying to give you an idea. It's hard to read here on the overhead.
That's the one part of that display I understood.
Yeah, right. It's trying to give you an idea of what kind of machine things cause variability in what kind of areas. That's all it's doing. It's trying to say, mechanical condition typically causes variability in this region, pulsations in that region, stocks in this. That's all that is. Just to give you a hint about where to look. If you see a variability here, it might be related to that.
Okay, so that's what that is. Now these graphs, one thing I hate about these graphs is this is my 3 Shades of Grey graph. This is what that movie is based on. No, it's actually 3 Shades of Grey. It's a movie about control analysis. But anyway, it's what happens is you define ranges of variability. There's a monitor window here that you can go in and set up these ranges. And what it's doing is it's basically splitting up the signal into variability bands.
Okay.
And telling you, first of all, plotting a trend.
In space.
What?
Is it where it tells you where that variability is located?
Oh, it tells
you the relative amounts
magnitude.
of variability within that band.
The magnitude within
Magnitude. So these are like speedometers.
Okay, and if
So-
you hit red, you're in trouble.
If you hit red, you have a lot. Well, it doesn't mean you're in trouble. It means you have a lot. See, this is where this is a little...
You're setting a threshold inside
Look
there.
at the power spectrum accumulation
Yeah.
you talked about, and this is in the controllable range. This is trying to just visually break the little 5-minute trend windows.
Yeah, into 3
stuff you
pieces.
can observe.
Yeah, 3 pieces. So that's a range. That's gray. That's grayer, or sorry, that's gray. See? Light gray, light gray. That's grayer. That's grayest. Okay? So what it's saying to you is that all the variability in the signal is broken into these 3 pieces. When you plot them trend-wise, you see that this dark gray is a little more than half.
Yep.
This medium gray is maybe, to me, looks like a quarter, perhaps.
Right.
And this light gray looks about a quarter-ish.
Right.
So you're getting, and they're all additive.
Yep.
Where they get hard to interpret is when it looks like that, and you've got, and you've got lots of this, but very little of those, so you can't even see them in the graph.
Right.
Not maybe presented in the best fashion, but that's what it's trying to show you is the relative amounts of variability in the different bands. It's like a 3-point power spectrum, if you will.
So when I look at the number 3 area there, I can see I've got most of the variability is occurring in that range.
34 seconds to 300
And then
seconds,
I
which
can
for
take a
us,
look at the chart at the top right and say this could be a potential source of it.
right. The other thing is, in this case, that's to have lots of variability in the 34 to 300 second range is probably good for us because we're likely able to fix that because it's slow.
That's right.
If it was the other way around and all the variability was in this 2 to 10 second
Yeah,
range
you can't do anything.
and none was over there, then our MD controls aren't going to do much with that. But then that would lead us to say to the mill, okay, that 2 sigma, the 2 sigma is still going to show that, the variability. We can't fix it with MD controls. However, there's some high frequency wet end stuff going on that you guys need to look at in your DCS, which could be our DCS.
And
it
we
might be
could
our
use
fault.
the IQ select to further narrow that down by doing some...
Yeah, or you do power spectra, you know what I mean? You can
The other good thing
point
about
into
this,
things.
though, in your example, Jay, actually that's good for us in terms of profiles, because there's not a lot of high frequency
Right,
information
that's
that
right.
we do in profiles.
Right, so therefore we can fix it.
Right, okay.
In this case, because it's like that. Like I said, this is good for us because it's fixable. You know?
Got it.
So
I wouldn't use this for before and after things in a report, because
No,
it's going to
no.
confuse the hell out of
The
everybody.
idea is you visually look at this and, whoa, this is the outside of normal, what's going on?
Yeah,
So it's a dashboard.
It's a dashboard, yeah. Okay, this is the MD trends, and what we have here is we have some MD trends, we have some power spectra that are calculated from them, and this here is a chart of the top 4, the four frequencies with the highest variability in them. Yes, John Pressman.
I have a question for you and Stephen as well. If you upgrade a scanner, an old scanner, to the new IQ select, you won't be able to get those tools, right?
No.
If you do upgrade the
Not
drive,
unless you need the web moisture, that is key. IQ web moisture is key to doing these analyses.
Well, there's the fast and the slow. You can still have the slow without wet moisture, but it's not as
Why do you need
valuable.
web moisture?
Well, there's two
Because
versions
these
of this.
applications, we count on you having web moisture.
Which provides a fast enough signal, or what?
But there's a fast and a slow. The fast one, without you need wet moisture. Otherwise, you got nothing. But the slow,
These applications get generated with web moisture.
but they would work on the slow too. They should work on the slow, the
But are
normal.
they only looking at moisture?
No, they can look at weight.
They're getting the signal, and especially for the advanced
There's
applications, it's a choice.
Yeah, for the advanced applications, there's a fast speed one, which you have to have wet moisture. But for the basic, you can use the slow speed one, which is supposed to look at the regular data.
well, even with the basic, if you didn't upgrade your drive, and you have the market, you need to get the new drive, right? You get out.
Oh, yeah, scanner has to be select scanner.
Yeah.
Yeah, but very good paper ID to select.
Yes.
Well, that's,
That I'm not sure. Yeah.
I talked to Rick the other day, told me he's got it set up all.
Yeah.
The MetzoIQ Basic, are these available only on our operating stations or via the email on the web?
No, only on our operating stations.
Only the operating
Yeah.
stations?
Yeah.
What do you mean?
Because you can,
We can also remotely access that.
Okay, should be in the superintendent's office too.
well, if he's got a
Oh,
DNA view server.
yeah.
Yeah, you can have it anywhere.
Yeah.
He can look at it from home in his jammies if he's
How
got
much
remote
is a
access.
DNA view server cost?
Same as an operating system.
Yeah. So one thing I want to mention about this here, about these, they're called main periodic components.
You don't want the mill manager looking at this.
Okay, those main periodic components are the top, the 4 frequencies with the highest variabilities are conveniently plotted there for you. And Trend Tool, for those of you familiar with our tool, Trend Tool, it does the same kind of thing. It actually plots the top 10. However, having said that, this is a dangerous thing. Because if you don't know what this is, people assume that those top 4 are actually A, significant, B, need to be fixed, C, can be fixed. And that's not always the case. We got into trouble at Jessup because someone was reporting on the top 10 high periodic components that they got on Trend Tool when they do a power spectrum. And then one day the mill looked at the report and said, so have you fixed these 10 things? What's causing those? And some of them were just high frequency spikes. And all this is doing is it's finding the 4 biggest spikes and putting them there. It doesn't know if they're significant, controllable. All it knows is they're the biggest spikes. And sometimes the biggest spikes can be fixed and sometimes they can't. So use that with care, I tell people. Don't just blindly put it out there without an explanation.
Again, it's all customer expectation.
Yeah, because then they'll think, oh, you've highlighted what you're going to fix? Great. Show me next week once it's fixed. Well, you know, and it's not what it is.
But
So anyway.
ideally, you could say to the customer, hey, there's a 53-foot cycle.
Yeah, right.
What's going on?
Yes, and you can. And then there's, well, anyway, there's more displays than this. And this is the other one where you put the 53 feet in. And
I'll be in the classroom.
Okay, and there's that too, but I don't go into that now.
Jay,
Yeah,
it's after 5.
I know.
So
We are.
we can keep talking. But
So Jay, go to Jay.
Yeah.
Click on the chat button that's flashing. Just for a laugh for everybody. Go down. There. There you go. Click on that, and then click on the live link down below. See there you go. Click on that. Yeah.
Okay, so I think it's only fair to say there's a lot of interest in this, so let's continue.
Okay.
But those who want to leave,
Yeah.
I think, in fact, I have to get going.
Yes.
Finland find its drive.
He must have fun. That's why.
Don't you guys want to live in Finland?
I have a great story about this, what I did to Andrew Stein. Did I tell you that?
Very good, Jay. You can keep this.
Threw a pencil at him. I know that.
I'll give you tonight.
You're in $7 million. Wow.
Anyway. Yeah, how do I get back to? Yeah, exactly. Well, I was looking at that thing that was 53 feet long, but I think that was a felt.
Let's move. But yeah,
Okay.
that's right. Let's continue. Before I leave, I want to just say thank you for staying. We're going to do more of this because it's obvious that what I wanted to say there is we've done an awfully poor job organizationally to get onto these unique things.
Concepts.
I
mean, if everybody that did QCS knew really understood
You know what, George?
or even if just a project, if I had understood this, it would have been on every one of my scanner deliveries.
Yes,
no questions asked.
It was also the desire. That point came up during the discussions.
There was a lot of effort placed on this in 2000, 2001, 2002.
And Dave Lang has given a lot of...
99.
Yeah,
I never heard of it.
No, but Dave Lang did a study, and not a study, but I asked Dave, I said, put something together, okay? Get all the information, because they said, oh, we don't really see the usefulness. We don't have the appreciation. Okay, here's an appreciation, but nobody wanted to listen to that. organizationally, management didn't push.
Yeah.
Management didn't understand
I
what
wish
the
that
hell
somebody
this
would
is.
have told me
This is
that
gonna be
this
different.
has to be done.
Exactly
That's what should have
that.
been said.
Right, so there was no leadership from management side
Yeah.
to do this. And I'm so glad you guys are here, and Tim understands it, because we went to Plymouth, he was the account manager, and Plymouth, we have examples from there. So we have a
But
great
until
tools
this
here.
very afternoon, I didn't see.
And I know that, and in fact, Mr. Lee Sherrill,
And Lee was trying to call, Lee's just a salesman.
now wait a minute, he came to, how many hours did you drive to come to
Oh.
the meeting?
Oh, where was, I was in Oklahoma.
Yeah,
I
tell
drove-
him the story.
I drove to Atlanta. Almost, I stopped, spent the night, got up and kept driving. I think I went 900 miles. And the point was to prove to Atlanta, to the bosses, how important I thought it was. This is what we needed to be doing. And I wanted to deliver that message to territory that's review.
Yeah, he came for a territory
Where was
review
that?
several years ago.
The hell?
See how we're missing the boat?
Yeah.
Yeah.
You know,
I
if they're
don't-
gonna be a better company,
I don't think that we have been much territorial issues.
no, but why not?
Yeah.
Oh, we would,
All the service.
But it should have gone, you know,
Why
Yeah.
was there no interest in
yeah, I don't
doing this?
understand.
Again,
The last
it's an organizational
10 years.
issue, it's a leadership issue, has nothing to do with,
and it's not that there is no interest. When Chuck was pushing this thing because of Julie at Simpson 2 years ago. So we verified that it's there, everything is done because of this general. It is not that there was no interest, but we just didn't know what.
exactly.
And it's not just North America, because a friend came out from Finland at Fort Hudson, and I asked him about this, and he laughed at me. Oh, nobody does this stuff. We don't know how.
That's sad.
It is
Yeah,
sad.
it is.
By the way,
Okay.
he gave 900 miles here, but when we were in Finland, I had him talk to, I don't remember who at that time. So we went more miles, and in Finland, he said the same thing, he made the same point.
Or somebody?
I really
not-
don't want to
yeah, I did.
look like an ass.
Yeah, okay. All right, let's move on.
Anyway,
Let's
move on.
move on.
Thank
We
you.
identified the problem.
You can grab this when you're in trouble.
Thank you.
Thank you, Dave.
Fixed, but it's recognized.
It's recognized. It's
done.
first, it's step one. Step two is train some more people, and step three is do it. Anyway, this is the same kind of graph as my high-low res graph, except instead of it being high resolution and low resolution, this is related to the speed of sampling. The blue graph is a 5-second sample with the scanner and fixed point. So let's say that sees a lot of the variability. Maybe a 1-second sample sees more, but anyway, we did it with a 5. The green is seen
And
by,
we're looking at MD now.
we're looking at MD and we're looking at how fast we're looking at the MD data.
Yeah,
So
got it.
fixed point is the fastest,
Of course.
5 seconds. Then we have two scanners. We have the old scanner and the new scanner. Where we have the scanner that takes 45 seconds to traverse the sheet versus the scanner that takes 22 and a half to traverse the sheet.
Yeah.
Right? And so green is the fast scanner, the new one, red is the old. Once again, look at the two segments. The guy that looks at the data fast enough, or faster,
Sees
has the
more.
high, sees more, has the higher two sigma.
Yeah.
Anyway, okay. And then from a power spectrum, same idea as the other graph. If we assume that the blue, the fixed point is the whole truth, which we know it's not, but let's assume it is, the scan average only sees this much of the variability. And the old scanner only saw that much of the variability. So scan speed affects this too.
Same principle.
Same principle, not just resolution.
Yep, got it.
Okay. This is the scanning logic to help you set up this variable speed scanning. Okay, this is one of the pages under the scanner, and there's all sorts of setups you can do here. You can do things like different speeds after breaks, after off sheets. You can create this, you can use this analysis mode. You give it the speeds you actually want it to scan. You can turn this whole thing off and on.
Yeah.
You can tell it to go to fixed point periodically and do analysis for a fixed amount of time. This is the whole setup of this, which...
Now, I know there are some recommendations, like when you're trying to help, they're trying to help thread up that put in the
Yeah.
scanner and some type
Well,
of
short scan.
short scan or something like that.
Yeah.
Or, you know, I wonder, is there any type of list of recommendations that we could really optimize?
There, I don't know.
I don't know if
There's a list.
sales writing is going to be specific to the machine, whether they can use it or not, or whether it's even important.
Okay.
Okay. The reverse and forward scan sheets probably always want to try and set up, because if there are empty cycles that come along,
We want to.
you're putting the defense in place.
Right.
What Richard also likes to do is to set up a fixed point interval to run every 4 hours, for example, so it gives a history of event frequencies are
Right.
showing up.
In the
coming
fixed
and going,
point.
and whatnot.
Yeah.
Very good.
So I would say, you know, the transition stuff might have to be under operator control, but definitely
This thing.
yeah. If we have automatic rate change, we might actually consider getting it to kick in for automatic rate change, to get the faster scans, so the control is better.
Those type of recommendations would be useful for
Like just written down.
a default setup.
That's expensive.
You know, start
Yeah.
here,
Yeah.
and of course it's subject to change based on no requirement. But these are good
Write me an email
if
about
you
it.
don't do anything else.
Or write down on a piece of paper and tell me at the end, so
No,
I write it
I'll
down.
send you an email.
Okay, because I can't write it down, but that's a good point. And we know what these are. You know, a 5-minute discussion between me and Richard and Steve Bale, and we write it down. That's how long it takes to do. It's
Yeah,
not
I
a big deal.
understand. You just have some practical experience.
Yeah,
understand
and just some
a little better.
We don't
rule of
have
thumb.
anything. We
Rules
don't
of
have
thumb.
anything against doing
Rule of
things
thumb.
better.
I'm going to call it recommended default settings.
For this, yeah.
What about a website for the help page?
Well, I can't make Capray change the master software. Not a bad idea. Not a bad idea, because the CD and MD controls tuning pages now have these help windows like that you can click on them, and it kind of tells you the steps. So the concept is good, but I can't make them put it. I mean, I can put in a tech note suggesting it gets done, but who knows how long it's going to take to get done. And then all the existing systems won't have it, right? It'll only be from now. I guess you could customize this, yeah. Actually, well,
Anyway, that's fine.
yeah. Anyway, that's what it is.
Yeah.
Something I want to talk a bit about MD and CD sampling for lab testing. Okay. Ideally, so you're doing MD strip samples for your sensor correlation. Ideally, you want to do this so-called A and B sampling. And the idea behind the A and B sampling is that you're taking samples as the picture shows on either side of the reel. You run them, you measure them both in the lab, and you get a 2 sigma between the two measurements. And if that 2 sigma exceeds a certain level, you throw the sample out. And what the check here is to check the repeatability of the lab analysis, because the last thing you want to do is correlate your sensor to a lab that's crappy.
Yeah, yeah.
And if you were only, and we've had this happen.
This is document error standard.
It is, but a lot of mills don't want to do it. And they say, I'll just take one, we're good.
No, and you're taking both sides because that gives you much variability on the outside of the roll, right?
No, you want you're taking both sides.
So they should be very similar.
Because they should be very similar, because they're not far away from each other, really.
So if those samples are too far apart from each other, then you know that.
Oh, okay, so now you know it's lab-induced variability.
Right, versus sensor-induced variability. And if it's lab-induced, throw it away. Or product. If it's a lab-induced variability, get rid of it. So that's the point behind this. It works for ND, it works for CD, same concept. You take a CD strip sample, take another one, do 2. Again, I've had mills refuse to do this because too much work, we're good, blah, blah, blah. And maybe sometimes you have no choice, and they won't do it, you can't make them.
There are some times where it's not safe to be on that.
Yeah, okay, but be aware of it, and be careful.
But what you still do is you cut your sample
In half.
You might take not front side, back side, but you might take 2 off the front.
Yeah, or like an up and a down, like a here and a here.
Exactly.
The idea is get two samples of the same thing and let them run it through twice and hope to hell they get the same number. And if they don't, you're aware of an issue. It might have been a one-off issue.
Yeah.
It might be a shift-related issue. When Billy Joe Bob does this, he does a terrible job. But when Alan does it, it's perfect.
On moisture test, you're going to see them come in within 0.1%, 0.2%. And if you're going, and all the samples are 0.2, 0.2,
And then another one,
0.2, and one of them's like 0.7 apart.
Don't use
then
it.
you go, and you throw away the sample.
Yeah.
And he stuck it under his armpit.
Yeah, I've seen that. You know.
I know.
Or the sample touches something on the scale.
Right, exactly. So this is just a check and balance to make sure you're not getting a problem with your sensor correlation. Okay?
Because if you think about what this whole sampling process is doing for sensor correlation, the real variability is that blue line.
Yep.
The fixed point samples, whether you take, the scanner readings that you take could be 1 second samples, these dots, could be 40 millisecond samples, but the bottom line is that what the mill is testing is that little yellow square, which isn't what you're measuring.
It's just somewhere along that.
It's somewhere along the line.
Yeah.
So right away there, even if everything else is perfect,
Yeah.
there's an error because of that.
Yeah, of course.
Okay, and just understand how that contributes. Now, someone asked me about guarantees. Chuck, I think, said about guarantees. Okay, lots of different MD control guarantee approaches. These are the most common ones for MD. There's some percent improvement where we say, you know, your 2 sigma is going to be 10% better. But what you need is baseline data or an on-off run after the system's in.
And you need to consider how that baseline data is collected.
Right,
and
and and what exactly. So, you know, you're good, George.
I'm learning.
Yeah. Okay. The other one is the reel-to-reel absolute 2 sigma number. So you say the reel-to-reel 2 sigma of the real average basis weight of the low resolution will be 0.6. That is a nice thing to guarantee because it gives you a small number. Because if you think about a real average profile, what's a real average profile?
It's the average of the whole reel. Right?
It's an average of many. It's the average of the whole reel, all the profiles in the reel.
Right.
Right. And so that resulting profile, the highs are gone, the lows are gone.
That's totally,
But the number looks good.
Yeah.
It's tiny.
Yeah.
So it looks good. So sometimes that's a guarantee that you may be forced into using in your thing because your competitor is quoting a guarantee that way because the number looks good. Well, because my 2 sigma is much smaller than his.
But are you comparing one reel to another reel, or are you comparing the average over
You're
the
saying
reel?
the average of the reel,
Of a reel.
of a reel will be less than 0.5. I don't care what it is
But
now,
you
I
need to
promise.
specify how many reels that would
Yes,
apply.
and you need to specify what grade and if there's any conditions, and it can't be off.
No breaks,
okay.
no breaks.
Okay, weasel words.
Yeah.
Sometimes, well, very rarely, I think we use this MD 2 sigma absolute number. Maybe we use it sometimes, but not so much. Lately, the most common one is the percent improvement. The second most common is this one. I think the third most common is that one. And weasel words. So percent improvement provides some protection if the original situation is worse than expected. But sometimes the baseline is difficult to collect because it's not comparable or you can't get it or blah, 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 as we just said. Okay?
That's easier, the percent improvement's easier to translate to dollars.
Right, right. But maybe harder to get the before and after.
Sometimes you're doing it with old scanners.
Yeah, and it's not directly comparable.
Yeah, you can't compare apples and oranges.
Right, exactly. You keep going from noisy sensitive or sensitive. Very
This-
slowly calibrated, so it's really what's showing the true
reality.
True reality.
Or a
yeah,
competitive
it was
system.
Yeah, it was competitive. Let's say moisture was truly ranging between 5 and 8, but it was only showing between 6 and 7.
Yeah, yeah.
It wasn't seeing the 3% range.
Yeah.
It was only seeing 1% range.
Looks better than it really
And
is.
it looks way better than it actually is.
Yeah. This is this reel-to-reel, very traditional approach. The numbers look tiny, but as we said, you know, in one sense, it's good for us because it's the best protection against uncontrollable variation. All that fast stuff that we can't fix is going to get averaged out.
Built in.
It's going to be averaged out, so you won't see it.
Yeah.
But is it really the reality? You know, is it? It isn't. So, the scan average is really the best measurement, the closest to the truth, but we don't use that a lot. So it's just a 2 sigma scan average values. Because that's what you're actually controlling. You're controlling the scan average. You're measuring the scan average.
And these are controls guarantees.
Yes, but there's a.
You only postpone it for 10 minutes.
Okay, I've never even seen it pop up with that before. Maybe I've never had my computer on for 2 hours at a time. I don't know.
Yeah.
Anyway, higher risk because if there are high-frequency process problems that our MD control cannot fix, it'll still show up in the 2 sigma, but it's not our fault, or we can't fix it. So this is a higher risk guarantee. Weasel words. Okay, MD controls are designed to be steady-state regulators and should be judged Data is to be included from reels where current and previous reels have no set point changes, no breaks, no grade changes, 100% on control. Reel elapsed time is reasonable.
So it's not a short reel.
Yeah, if you get a reel that like runs six minutes,
Yeah.
something going on, or worse, or you get a reel that runs 2.5 hours or 3 hours.
Yeah.
Don't use that reel. Don't use that reel. Okay, and free of external disturbances outside our control.
Yeah.
There should be limits, or whether it's by time or by grade.
Yeah, and then a period over which period will collect those.
That's the time limits.
Yeah.
So these are, but I mean, the thing is, this has to be written in the sales contract. And
It's
these words are
amazing how many
excluded.
times
And
it's
this
not.
has been going on for 20 years.
Yeah.
If the words get missed, if someone forgets to say 100% on control,
Or they don't specify the grade.
or you don't specify the grade,
It's always.
It's all grades.
it's all grade.
grades, yeah.
And you know, I've
And then we
seen
gotta
many.
wait for them to run.
I've seen many cases where people have collected data and haven't bothered to look about the on-control part. And there's crappy data in there because it's not on control and nobody notices it. So you've got to watch these things. And there is a recommended test
Yeah.
for the guarantee.
Yeah, I know it well.
Yeah. CD control, similar ideas. There's a % improvement. There's a strip sample absolute value, which is what Valmet paper uses.
That's a tapio.
That's a tapio thing.
Yeah.
Okay, that's what they like to use. And if we have a machine guarantee with them, then that's the guarantee we're held to.
Yeah.
The only problem, we'll get to the problem with that one. But, and then there's a real average CD2 sigma. Typically, real average actuator zone, not high res,
Yeah.
actuator res.
That's
and-
all we can control. is
Okay,
actual.
and error profile, not measurement profile. Because CD control, I'll tell you why.
Yeah.
CD controls have the ability to control to a target shape that is not necessarily flat. If you put a target
you
like
want a
this
frown,
in,
yeah.
you put a frown in.
So it's
it'll-
error, it's a variation
Yeah.
from set point. is all
Yes,
we care about.
if you do it on measurement and they put a shape in, the two signal will be high, and it'll look like it's bad, but it's not bad because the error will be zero.
And by the
So
way,
be
the
careful.
two sigma you see on our control display is the error profile.
So it's not an absolute weight variability or anything like that, it's an error.
Yes.
From
Error from
on
target.
all of our displays.
No, only on the CD control.
Yeah.
Oh, okay.
So sometimes you'll see on the CD control page.
But when I'm looking at a weight display on
If
the
you're-
overview,
If
it's
you're on the
actually
overview, that's on
counting.
the actual profile.
Measurement.
You'll see is a difference. You'll see if there is a very distinct shape to it, sometimes there is, once you're on the calendar or something, then you'll see control profile has two sigma very small, but
Because
the
it's
regular profile
Has a
the
bigger
operators
one.
look at
Big one.
has a
However,
bigger-
unfortunately, they're both labeled CD weight 260. But they're different. What's wrong?
Yeah. I
They're
got it.
both profiles. What's wrong? Why aren't they the same?
Good to know.
Okay. Again, there's weasel words. The % improvement. You know, sometimes you can't get the baseline. Definitely profiles from different scanners are dangerous. Sometimes you can use CD strips. The strip samples is the normal approach with Valmet. You know, they select a few grades. They do one sigma instead of two. I don't know why they do one sigma. That's what they do. Okay, it's typically independent of the gauging vendor.
Yep.
It's very good for benchmarking. The problem I have with this is they take samples and they send them away to a Tapio analyzer sitting in Finland somewhere for analysis, which takes weeks and weeks and months. By the time they run the samples,
It's
our
not the
system
same.
has broken 20 times already, and a new project manager assigned to the job, and your boss is yelling at you for not closing the project. So you'll die of old age before the
Yeah, I
samples
know,
are
it's always.
That's my problem with this. If they could turn this around in a day or two, great.
Yeah.
But they can't. It takes them weeks and months to turn this around. And so I hate when I had projects with this kind of a guarantee
Well,
because I was never
actually,
going to close.
I've got them to sign off on the project.
Like Metso signs off from you.
Yeah.
And then they deal with the
And
customer.
they deal with the customer.
Yeah.
And then I budget a little contingency to go
In
to
case-
service.
In case they
you gotta
call
come
you.
back and
Right,
return
yeah. Anyway, that's just to be aware of it.
Yeah, that's how you get out.
The real average profile, again, remember actuator resolution, not high res.
Yep.
And remember error profile, not measurement profile.
Yep.
And sometimes on multi-grade machines, you'd want to express this in terms of %, not absolute 2 sigma, right? Because if you have a large grade range, you know, 2 sigma.
Yeah, it would be very significantly from grade.
Yeah. So sometimes it might make more
When
sense
you
to.
say percent,
So,
that's
basis-
percent of the full range.
Right, no.
No,
If you
percent
have
of
an
measurement.
average, if you have an average of, say, your basis weight
You
is
said
70,
Seven,
Yeah,
okay.
and your 2 sigma is 1, 7.
Okay, that's 10%.
That's 10%.
Okay.
And on the next grade, that's a 40-pound grade, your 2 sigma is
Four.
still 7.
At 7, then you're
That's
screwed.
a
But
20%.
If it's 4,
It's still the same, yeah. So that's what it is.
So it's relative to target size. Okay.
Yes.
Okay.
And the same kind of weasel words. The only other weasel word we add in CD is that existing CD actors have sufficient range.
Yeah, you gotta have the horsepower.
Right? You know, the horse, Dave mentioned that earlier.
Yeah, and if
know
you
the
show it how to
horsepower.
range, then you're done.
Then
That's
you're
all
done,
you
yeah.
can do.
And a recommended text. And it's important that performance guarantees have some kind of remedy or limited liability.
Yeah.
Okay, that's the lawyers talking, you know.
Yeah, and it,
That's all part of the contract.
Yes, that's what the salesman should be listening to. The salesman should be listening to this part.
they always have.
The salesman in blue shirts
No, this is
leaning on the wall should be listening to this part.
Yes.
Okay, or to the prairie. Okay, this is the performance guarantees, right? The recommended text for controls, what they should say, and then the legal liability limitations. Guarantees and remedies are exclusive. No others apply. Limit liabilities of consequence or damages, etc. Need to be excluded. All this legal lawyer talk should always be in these guarantees.
But Jay, at the same time, right, do we maintain a set of official guarantees?
I don't think so.
Oh, no.
Hell
I just
no.
copied the one that was given to me 2 years ago. And you
Yeah, hell
We
to
should.
the no.
Yeah.
We have very good documents. Obviously, case by case, they need to be tweaked.
Yeah.
But I don't think that we should ever have to start it.
No,
If
you
you
should.
look at my contract reviews for the last 5 years, you will find that 80% of those that the guarantees were incomplete or inadequate.
Yeah.
That's
I'm not
why.
kidding.
I know. And this has been going on for 20 years.
We are working
So
on
you
that.
would-
Yes. All
No,
right.
it's up to the salesman. Anyway, sorry. So what's next? Better understanding of paper mill economics and ROI, how our equipment contributes to that. We talked about that a lot in the last few days because we can use this. Okay. One of the things I have in the course here is I talk about the reality of a paper machine efficiency. And this is obviously very simplified, but you know, that's a scale of profit, that's a scale of production. If they could somehow run the machine 24/7 at their maximum design speed
Right.
in an efficient manner,
They make that
they'd make that much money. But in reality, there's some losses, there's idle times, there's shutdowns, there's maintenance, there's external reasons. They don't always run at full speed. So in reality, they can only sell this blue box, which is less than the theoretical maximum.
Sure.
Our job is to try to look at these other boxes and see if we can help them in any way
Make them smaller.
and make those boxes smaller so the blue box gets bigger. Exactly. Okay? Maybe we reduce their costs. Maybe we can get the machine to speed up a bit. Maybe we can reduce brake time. Maybe we have less brakes. Maybe
More on grade.
Or more on grade. Maybe we can prevent some shuts, some unplanned shutdowns by having a Sensimex system so nothing breaks on the fly. You know, things
Or
like that.
picking up a belt that was 53
Right.
feet long.
Yeah.
That
So,
need to be replaced.
you know, you can get humongous ROI by changing these machine-related parameters.
Okay.
Or
Yes.
implementing a target shift.
Or implementing a target
That's
shift.
reducing costs.
That's that's reducing cost, implementing a target shift.
Okay.
But I should probably edit this to say reduce costs and put in brackets implementing a target shift. Yeah. Okay. Here is a very simple paper maker's earning formula where we talk about things like, you know, we have certain machinery and there's a speed and a trim and an efficiency and a weight. And then based on raw material prices and production costs and energy costs and blah, 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 we come up with a profit.
Right.
Now, we cannot affect all of these points, okay? We can certainly affect machine speed with some of our offerings. We can affect efficiency or runnability with some of our offerings. We can affect raw material usage, target shifts. We can't affect the price or the salaries they pay for the employees. We can't affect what power
Market
costs.
price for the stuff. Right?
Yeah, right. So we can only affect some parts. We need to target those parts and look to see how our solutions can help the mill achieve savings on those pieces.
Might be able to affect their energy consumption.
Energy consumption, but not price.
Yeah, consumption we could affect.
Yeah, consumption, which is underneath there, I guess. Anyway, so that's
Good job.
that's the deal.
Very good. Very good.
Really good. And so, in my opinion, I would hope that every salesman, every service manager, every project manager would attend this 2-hour course.
I think they should.
Okay, and as far as the 3-day course, that's something for every project engineer or almost every project, or every QCS project engineer, and most of the service guys as well to attend.
It is really interesting. From the first time.
And I mean, I wrote this course originally in 99 or 2000.
Just in terms of broadening their breadth.
Well, I